Okay, great. So welcome, ladies and gentlemen, to our 6th session of the virtual conference on epistemic uncertainty in engineering. We have a really exciting series of talks today. We're on the topic of Manifesto on uncertainty. We have Professor Aven, Professor Ferson, and Professor Worden here with us today. This event has been organised thanks to the University of Liverpool, the Institute for Risk and Uncertainty, in a collaboration with the University of Sheffield for the Digital Twin programme, sponsored by the UKRI, as well as the Society for Risk Analysis that's helped to support the organisation of this. So we have a few more talks scheduled for the future as well. So just to note for people to write into the calendar, we have Uncertainty Arithmetic on the 17th of March with Didier Dubois and Laura Swyler. We have Admitting What You Don't Know on 25th of March with Gerd Gigerenzer and Anne Bostrom. And then we have another one to be announced, which it looks like this one might be in April. So we'll keep you updated and send an email via the mailing list. So our agenda for today we'll be starting with Professor Terje Aven at 2 o'clock, which is already now, but we'll start in a second. Conceptualizing, representing, and describing epistemic uncertainties in risk analysis, followed by a Q&A. We'll then have a wombo combo of Say What with Professor Keith Worden and Professor Scott Ferson with Q&A, followed by an open discussion on can we agree on anything about handling epistemic uncertainty in engineering. That'll be an open discussion where everyone can feel free to chip in. As I just stated, don't feel like you have to ask them permission to chip in the open discussion. Just unmute your microphone and get involved, or write things in the chat, and we'll try and read those out. So I'd like to introduce our first speaker, who will be Professor Terje Aven from the University of Stavanger. I believe I'm saying that correctly. He'll be presenting his research, as I said, conceptualizing, representing, and describing epistemic uncertainties in risk analysis. Terje is a professor of risk analysis and risk science at the University of Stavanger, Norway. He has many years of experience in industry risk analysis, and is the author of many books and papers in his field. Covers a broad range of topics in risk analysis, in particular foundational issues related to risk and uncertainty assessment and characterization. He's also the president of Society for Risk Analysis and the European Safety and Reliability Association. He's also the editor-in-chief of the Journal of Risk and Reliability and area editor of risk analysis. So he has a lot of amazing credentials and great experience. I'm really looking forward to hearing his talk. So let's please welcome Terje Aven, and would you like to start sharing your screen?
Yeah, thank you. Thank you very much for this introduction. You can see my slides now, and I put it on the view. Let me see. Now, should it be okay?
Yeah, we can see that perfectly. Thank you.
Okay, good. So thank you again, and I really look forward to a good discussion about this topic. I would like to say that I've been discussing the issue with Scott Ferson a lot, going back to 2009. I think that is a good story. Sorry about that, Scott. I think I would like to say that because I submitted a paper in Risk Analysis Journal in 2009, and it turned out that Scott was one of the reviewers. And he said, "My name is Scott Ferson, and you are Terje Aven, I'm sure about that. And I liked your paper, I loved your paper, but I disagree about nearly everything you write." So that was a good start. And he wrote 25 pages, comments to that paper. And I wrote back, I think it was 50 pages. And we had a very good dialogue. And I think the editor said, "Yeah, this is so interesting, we put it on the website." So that was an excellent starting point. And later we had a workshop in Los Angeles in 2010, I think, and we discussed the topic further. And I think that through that kind of discussion, we were able to see different perspectives in a more clear way. And maybe we don't disagree that much today, 2021. I'm not sure. Well, let's see. That would be interesting to have the discussion later. So I'm going to talk about uncertainty, conceptualization, representation, and description or characterization. So probability is a key concept, but of course we will see beyond probability. So I will not really go into much into inference issues, for example, Bayesian inference, using Bayes formula, etc., or decision analysis. Bayesian decision analysis, robustness, resilience-based thinking to meet the uncertainties. I will focus on the concepts and the characterizations of uncertainties. But I will, of course, relate, when I'm talking about what is a good characterization of uncertainties, I will look into the decision context. So in that sense, I will also address that issue. What is a good way of characterizing uncertainties to meet the demands or constraints from the decision makers. So let me give you an example to have something concrete to talk about. And I like this example from IPCC because it's not that perfect. Let's see. There are two statements here. First is a statement, and the other one is linking to an uncertain quantity X. So the first one is, most of the global warming trend is a result of human activities. Statement in one of the is really a key statement in the IPCC reports. And the second one, the global temperature will increase by X degrees in the coming 10 years. So this is quantities subject to uncertainty. So we have the X, it could be the temperature increase, or it could be 1, 0, depending on the statement being true or not. So it's uncertain. And I write it, conceptualize it at X view, X and U uncertainties. And then the next question would be to characterize that or describe these uncertainties of dealing with that challenge. Okay. I mentioned in the title the risk analysis and the risk concept. So what is the link between uncertainty here and risk? And to me, this is very much similar. There can be different perspectives on risk, but I would say according to modern risk science, it's not that different. Going back to Kaplan Garrick in 1981 in their famous paper on quantification of risk, is saying something also about the concept. Risk is uncertainty plus damage, or damage plus uncertainty, which is really the key, I would say, in current thinking about risk, as CU type is the consequences of the activity is C, and the uncertainty is U, which is very similar to XU. C is the future consequences of the activity, so it's unknown, yes, and subject to uncertainties. You can say that that is a different thing than the uncertainty XU, because X doesn't need to be about the future quantity. But in risk context, we also talk about different C's, not necessarily in the future. We talk about parameters of probability models. We talk also about the kind of cause-consequence relationship, where we're not really dealing with future quantities, but more underlying concepts. So it's really very much, I would say, similar type of challenges. So the next question is to how to measure or describe risk. Well, that would be really going into how to characterize, describe, represent the uncertainties in relation to that C. So it's very much similar when people are dealing with uncertainty characterizations. It's very much similar to risk characterizations. Okay, so going back to this example that I like so much, the IPCC, and it's written in that, I think it's the sixth, this report from 2014, the latest assessment report from IPCC. It said that it's extremely likely, at least 95% probability, that most of the global warming trend is a result of human activities. So the question is, what does this mean? It's a way of characterizing uncertainties, or is it a degree of belief, or what is it? And I think this is a really important statement, and it's having impact, very much large impacts in society today, this kind of issues, and therefore this statement is important. The problem is that IPCC doesn't explain what it means. And I think that if I would like to challenge you to, I mean, how would you interpret this statement? I will give my interpretation soon, but think about that. If I asked you now, what would you say? What is the interpretation of this kind of statement? How would you read it? And I think it's really important for the communication what it means, because if it has something to do with the authority of this statement, is it linked to the physical world, or is it some judgment about some degree of belief of some analyst? So it's important to know what it means. Here another example from a climate change report showing some density curve for the global warming temperature. And you see the center of gravity is about 3 degrees above the industrial level. Yes, so again, we can ask, what is the meaning of this? The report, if you look at the report, they don't say what it means. And for communication purposes, for using that in a context, we need to understand what it means. I come back to that. So in order to discuss this, I will ask you, is probability precise or imprecise or unimprecise a good tool for representing or expressing uncertainty? Well, to answer that, we need to clarify what probability means. Why do we need that? Well, because I would say that if you have a concept in scientific work, you should explain what it means. And also, as I had shown in this example, decision makers and other stakeholders need to know in order to be able to use the results properly in the decision context. I have another example from when I worked in the industry. I was presenting results to top management of the company from a risk assessment. And I had some probability numbers that I presented. And then one of the managers asked me, what do these numbers mean? And what about uncertainties? And I mean, he was arguing that I need to know this because I'm going to invest a lot of money partly based on your assessments. So I need to know what these numbers means and what uncertainty in this context means. But I could not really at that time give a good answer. And if you ask analysts today, uncertainty analyst or risk analyst, the same type of questions, I have to say, I've done it, that not always people are able to say what it means. And therefore, the communication is really poor, and it's difficult for decision makers to actually understand what the results are saying, and seeing both the strength of the message and also the limitations of that message provided by the assessments. So let's take it slowly here, because we have a lot of time, and sometimes it's good to look into these different type of probabilities slowly. I mean, classical, we can just ignore because it's basically only used for cases with a finite number of outcomes, and they have the same probability, which is not really often the case, except for gambling and things like that. So we don't talk more about classical probabilities. Also, the logical probabilities, what about them? I would drop them because I don't see any theory that is actually supporting it. I mean, the basic idea is that saying that for a specific knowledge, there is one and only one probability, the logical probability. That would be nice to have, but I don't see that is being justified in any way. So if one of you have an argument for why that exists, a logical probability, given one knowledge, there's one and only one probability, and you can give an interpretation of that, please send it to me. I have not been able to see it. Okay, then we have left only figurative probabilities and subjective probabilities. And we are all familiar with frequentist probabilities. The frequentist probability is saying that you have the probability is the fraction of time the event occurs in the long run. That's the underlying unknown, uncertain probability. It's reflecting variation, actually. Is it on or off, the event occurring or not? And the subjective probability I will come back to is this expressing some degree of belief, is epistemic uncertainties, and I will come back to that. So we have, the situation is this, that we have probability being used for uncertainty, imprecision, and variation. The same term is being used, which is problematic. And I'm also a little surprised to see that a lot of people don't care about distinguishing between whether you talk about this or that. And for me, this is, you cannot provide or establish a scientific platform if you integrate or mix this into just, I mean, the same concept. I mean, you need to be clear, are we not talking about a frequentist probability reflecting variation, or are we talking about an epistemic uncertainty, subjective probability? So this is the issue. Subjective probabilities reflecting uncertainty. You have imprecise probabilities reflecting precision, and then you have the frequentist probability and the probability models reflecting variation. So when talking about subjective probabilities, I see this type of interpretation often. If some people would like to interpret subjective probability, they often come up with this one or similar from the literature going back to 1930, 40, 50s with interpretation like this. So if the probability is 10%, it means that you are indifferent between getting $0.1 or playing a game which is giving you $1 if the event occurs or if the statement is true, and 0 otherwise. This is the type of reasoning. And I said, if we're talking about uncertainty analysis, if that is the context we're talking about, this should not be used. And maybe that's a provocating kind of statement, and let it be, because it is certainly that you have a mixture of uncertainty assessment and value judgment, how you like money. And I would not let that be a part of my assessment if I'm going to support or do a job for some decision makers. And my attitude to money is actually influencing the way I'm presenting the results. I say no way, should not be used. But there are alternatives, and some of you are familiar with this, of course, and one of the most famous advocator of this way of thinking about uncertainties is Dennis Linley. And I hope you have really studied his book from 2006 on uncertainty analysis. It's really nicely written. So the probability is 95%, meaning that the assessor has the same uncertainty, the same degree of belief for this event to occur or this statement to be true, as randomly drawing a red ball out of an urn having 100 balls where 95 are red. And this is conditional on a certain knowledge. And if you have imprecise probabilities, it's the same type of statement, but you have 95 or more are red. You're not willing to be more precise than just saying 95 or more. But it's the same type of comparison to explain what that subjective probability means, and it's conditional on the knowledge. And then we come up with the interesting question about following up question, is there uncertainty about a subjective probability P? Is there uncertainty about probabilities? Some would ask. Of course, there is uncertainty about frequentist probability. You can call it PF. Yes, because PF is unknown, and there's a reference of some underlying that is correct, and then you're uncertain about what that is. So there's no discussion about that. There's uncertainty about a frequentist probability. But is there uncertainty about a subjective probability, a probability expressing your uncertainty? That's another type of question. And I say, no. But there, in the way that I have talked about uncertainty up to now, it's linked to knowledge. But if uncertainty relates to I'm uncertain what I should choose of a probability or what I should do, that type of uncertainty, which is actually, I would rather call ambiguity or imprecision. I think we should use these terms because it's confusing when you're using uncertainty in that context, in that way also. So if the issue is about that I am not really, it's not easy for me to choose one particular probability, yeah, that is imprecision, ambiguity. It's not really uncertainty, at least not uncertainty in the way I've been talking up to now in relation to epistemic uncertainties. It's something else, being doubt, and there can be other type of terms, incertitude, and other terms that we can use for that, but it's different than the uncertainty I've been talking about up to now. So, is then probability, precise or imprecise, a good tool for representing or expressing uncertainty? I say not alone, not alone. And if you go into these examples here, absolutely, if that probability 95% was expressing subjective probabilities, was subjective. I'm not saying that IPC have that interpretation, but I think that is the only way that you can interpret it actually. Because you can't interpret as a frequentist probability in that you can't repeat the world to get some meaningful frequentist probability in this case. So it must be subjective, and if you have that kind of statement, it would not be sufficient, just a number. You need to have something also about what is the knowledge supporting that probability number? What is the knowledge supporting it? And the same with that curve. And if you have an interval here, from 2 to 4 degrees global warming, 95% prediction interval. Yeah, what is the knowledge strength supporting that would be a reasonable question. What are the assumptions? How strong are these assumptions? How, what is the basis for these assessments? And that is leading us to, I would say, two main challenges in relation to, in relation to this kind of issues. And number one is to transform the knowledge to the uncertainty measure or description. It could be then using precise or imprecise probability. And if you're using precise probabilities, it's absolutely subjective, that's no doubt. And it's more objective if you're using imprecise probability. And I'm sorry, Scott, I go first. I go back to our discussion in 2009. And actually, our discussion was very much about this transformation from the knowledge to the uncertainty measure or description. And I was saying that the subjective probabilities can also have some interest. If I'm working in industry and I ask the chief engineer, what do you think about that problem? And he's saying, or she's saying, 90% sure about that. It is providing some information. Another context is much more better to use a more objective description, an interval, imprecise probability, which is more really capturing the knowledge there provided. So it can also have, certainly also having both, because they are different, they are reflecting different things. One is more about a judgment, the other one is a subjective judgment, adding something to the knowledge that is actually there and documented, but it's not, if you're using the imprecise probabilities, you are more loyal to the knowledge that is available, but it can be not that informative. But anyway, you are not, and then they go into the second challenge. you don't say anything about that knowledge. It could be more or less strong and even wrong. And that's a part of the formula here. I mean, that's a part of the challenge of representing the uncertainties, because the knowledge could be poor. And the decision maker needs to know something about that also. Take an example here. We have an expert providing either a precise probability of 10% or an imprecise probability of up to 10%. Okay. And then it's transformed to this message here. But the problem is that this knowledge could be rather weak. One expert, and he could be poor. So we're having then a fantastic, nice transformation from the knowledge to the uncertainty measure. We are doing the right thing according to the procedures of uncertainty characterization, but we're not reflecting on the knowledge supporting it. And that's equally important for the decision maker and for the communication of that uncertainty, of the uncertainty. Well, I'm talking about knowledge here in a broad sense, justified beliefs, and the evidence in form of data, information, modeling results, and testing, argumentation, and so forth. Okay, and how do we look into the knowledge strength? Well, we have to look into the data, the information, the amount of data information, how relevant they are, assumptions, how reasonable they are, and the phenomena. Do we understand the phenomena and are experts agreeing? Have we scrutinized the knowledge that are there? For example, for unknown knowns, that's we don't have the knowledge, but others have it, and things like that. And this was done actually, I'm sure that many of you are familiar with the NUSAP system going back to a pedigree in the 80s and 90s by Ravich and Funovich. And they were doing something similar, looking into the strength of the knowledge, supporting the policy analysis, the risk assessments. It's similar type of discussions or reasoning. And this is just saying the same thing, formulated as I now said. Okay, let's take one step further in relation to that the expert is providing more at a frequency type of statement, 2 failures in 100 trials, for example, or up to 2 failures in 100 trials. Okay. Then we can transform that to subjective probabilities. Let's say P equal 002, P less or equal than 002. So we transform that, and we have the same type of case as we have already discussed. And then, but we could also, and this is interesting, we could also try to use that kind of knowledge to say something about underlying frequentist probabilities, PF, I call them. So what we have done then is to model the variation by that kind of frequentist probabilities. These are unknown. So we then can estimate them by these data, and we can discuss uncertainties about them using also subjective probabilities. And then we get uncertainties, characterizations of the underlying PFs. And there's a lot of nice theory on how to do that. It's part of the, for example, the probability of frequency approach is based on that kind of PF, and you're using subjective probabilities to express your uncertainties about that, using Bayes formula, and you do that. But you are not reflecting typically the knowledge strength that the subjective probabilities are based on, which you should also do to make it more complete. Yeah, so to express the uncertainties, I think that you need all of these to address all of these issues here. The probabilities, of course, and it should be precise or imprecise, and the knowledge supporting these probability judgments, and also the potential surprises represented here by the black swan metaphor. Because the knowledge can be also wrong, and how do you deal with that? That's of course difficult in the assessment because it's outside your knowledge, but you can do a lot to deal with that issue. And first you have to do is to acknowledge it. That's the first thing. And then you can do something. And a lot of work has been done in recent years to how to handle that kind of issues and improve your assessment. Of course, it also relates to how you are dealing with the uncertainties going into resilience and robustness and issues like that. But I won't discuss it now. So talking about risk assessment or uncertainty assessment is often said to be a systematic process to comprehend the nature of risk, express and evaluate risk or uncertainty with the available knowledge. Okay, so it's conditional on the knowledge. And this is the challenge. Of course, you can do sensitivity analysis to look into the effect of different assumptions, for example, but the decision makers for the total package of uncertainty characterizations, you need to also look into that knowledge. Is it strong? Also think about, should it be improved? If it's really this expert, only one expert, okay, it's so poor that these numbers that you're producing is not really interesting at all. So I'm saying that you absolutely have to go beyond precise probabilities. Imprecise probabilities you need, absolutely, but you also need to address issues related to knowledge and the knowledge strength. And therefore, I'm saying that in general, a pure quantitative approach is not sufficient in a practical context, because you always need to address the knowledge issues. Maybe that would provoke some of you, but okay, let's have some discussions. That's really good. So coming to the end, I just like to have this slide here because I think it's important to highlight that the assessments, whether it's a risk assessment, uncertainty assessment, or even a Bayesian decision analysis, is just an assessment and it has limitations and there are other concerns not captured. So there is something between that assessment and the decision. I call it often a broad review or something, a judgment, management review and judgment, or an evaluation. And I think it's so important to acknowledge that this is existing and is needed, because you don't go from assessment, you don't prescribe the decision from the assessment. There's always limitations. And I stop there. I have some literature here. So then I think we are ready for some questions. Are you there?
Thanks, Terje,
Yes.
for your talk and that lovely story at the beginning as well about how you and Scott first met. I thought that was quite funny, and I can totally imagine that. Does anyone have any questions that they'd like to propose? If people can raise their hands or unmute themselves.
Okay, I have a question. Thank you very much for the very interesting talk. Can you a little bit clarify, because you said that the usual kind of utility-based estimate of subjective probability depends on the value of money, but it doesn't matter. You can put $1, you can put, I don't know, a beautiful cup or some cap. Why does it depend on the value of money? I thought it's very similar to Lindley's approach, because when we are comparing $1, if, for example, it rains tomorrow, and $1 with probability 50%, aren't we comparing exactly the same thing, probability of subjective estimate of uncertainty of raining with the 50%, meaning out of the big ball, we pick up half red, where half are red, we pick up the ball. Why do you say that it depends on the money? We don't have to put it in terms of money. We can put it in terms of anything. Yeah,
okay. So this is a good comment, and I like that we discussed this because it's been actually not that much discussed, and I often get this kind of response, and so there must be something here. And well, I think this one here, I don't see anything else than uncertainty. I would call it a pure uncertainty assessment in relation to the event. but I would argue that this one, if you interpret this in relation to the definition I have here from the Finetti, I mean, basically the basic idea of that one from Finetti.
Oh, yeah. No,
Yes.
yeah. Okay. I got it. So you're not talking about utility. You're talking about definitive when he talks about amount of money.
Yes.
Okay. I got it. Yes, that's the wrong definition. I agree with you 100%. I agree with you 100%.
But you're right. You doesn't need to think in relation to money. It could be linked to utility. You absolutely
no utility. Yeah, but no. I now that I read attentively, I understand what you said. You're not talking comparing $1 if it rains with $1 with probability 50%. You're saying how much you're willing to pay. And that indeed is subjective. Yes, absolutely. Yes. Okay. And second question, I again, maybe I'm a little bit too cynical, but my understanding of climatology is that when I try to read the papers and when I try to read the report, I'm horrified. Are you taking them seriously? Because my understanding is what they're saying is somebody says, no, your numbers are wrong. And you say, this can be ignored. You're not a certified climatologist. How do you know somebody is not a certified climatologist? Because 95% of climatologists do not agree, and therefore you're not certified. So this is a big mess, and I'm not so sure why you use that as an example. I don't think they have, honestly, maybe I'm wrong. Maybe I should read something else other than this report, but my understanding is this 95% means nothing other than that they strongly believe that we should stop all the factories and kind of.
Well, I think it's we should be careful going into that debate. I mean, this is a pure uncertainty risk debate. I mean, if you have that kind of statement and it's actually being used, and of course we can argue why it's being used and things like that. And we, as the experts on uncertainty and risk, we should be able to say how it can be used and how it should be used if we would like to go on that path. And it's absolutely what I say that if you're going to have a statement like that, the only interpretation that I'm able to present and justify is that you have an imprecise probability, plus that you add something about the knowledge strength supporting that statement. And IPCC does something like that, but they have, I would argue, I'm sorry to say it, a lack of foundation. And they say, actually, you can't combine the probabilities and the evidence type of reasoning, which for me is just doesn't make sense. So I will not go into the climate change debate as such, but the issue of how to present and represent the uncertainties in this particular way. Thank you. Other comments or questions? I'm sure we follow up later also, because I know that Scott has some comments later in his talk.
We still have plenty of time, so I think Dominic Hose has his hand raised even.
Yes.
Would you like to unmute yourself?
Yeah, sure. Can you hear me?
Yes.
Great. Yeah. Well, thank you for your talk. And I have kind of a follow-up question here. So as I understand it, for you, subjective probability is more or less because it's ordinal in that sense. I mean, 2 euros is more than 1 euro. So that would kind of be what you get out of subjective probability, because you can't compare one probability of rain with the probability of a car accident or something. So why does it have to be probability then? Because you could take any other monotone measure as your uncertainty measure for subjective.
Yes, I think that's also a good comment. I have and think it's important that the tool we are using has some intuitive appeal, and it's also having a clear, crystal clear interpretation. And I've, in principle, open for any kind of way of doing that if you meet these kind of criteria. So if it's rather simple to use, intuitive, capturing this kind of thing we would like it to capture, and also having crystal clear interpretations. So therefore, and I just found this. I mean, if you have others that you will convince me, I've been studying a lot, but these are the one I think are precise and imprecise, helps me, but I'm open. And I really, as a researcher, I should be open for better alternatives. But of course, there are also good arguments for using probabilities that we know from the literature. Okay.
Yeah, so I mean, we can talk about this later, but I mean, for example, I'm not sure if I can actually get you there or if you wanna go there. But for example, if you take, so I'm working on possibility theory, which is maxative instead of the additivity of probability theory.
Yes.
And now the question would be, if you were, so in my opinion, the calculus is much more simple. And now my question would be if you'd be like actually willing to accept that. But we can talk about that later.
Well, I think it's I in a way, when I'm talking about imprecise probabilities, I mean the possibility theory is captured basically, at least one way of interpreting that. So I don't think that necessarily is a problem with using with seeing these two together.
Okay, thank you.
Thank you.
Is there any more questions? I think someone posted in the chat. No.
Could I just?
Adolphus? Yeah, Robin, please.
Yeah, just a quick one actually on the various definitions of probability.
Yeah.
Wasn't it the case that Dependencies and Ramsey came up with a sort of gambling analogies so that the laws of probability would follow? You know, if the user is then logically consistent, then you get the normal laws of probability following from this kind of definition. You could have another definition for a monotone measure, but it doesn't necessarily follow that that monotone measure follows the mathematical rules of probability. So I think there was a precise reason why they came up with this kind of language, even though it might not be a very attractive kind of language. And of course, the urn's in the pot, because that's really a frequentist definition. The laws of probability then follow from that kind of definition because it's based on frequentist ideas.
Mm. Yeah, I agree that I follow you on that. There is a fine justification within a certain context, as you are referring to, and then you are led to certain ways of doing it if you're into that context and you accept the criteria. And of course, this is partly, as I see it, motivated by an individual decision maker's sort of domain. But a lot of the work we're doing on uncertainty risk assessment is a context where you have an assessor doing a job, and this decision maker is some else person. So it's a bit different context also. But I still think that we need to be careful in having concepts that are having clear interpretations. And that is a requirement for, at least in a practical context, if you're talking about uncertainty assessment, engineering context, or whatever context, we need to be able to say what it means. And then it should be meaningful, and also in a way that is not disturbing the separation between the uncertainty assessment and the decision-making context, if that is important for your context.
No, I think I completely agree. And I think, you know, the point I was trying to make is that you do want these measures to satisfy certain mathematical laws so that you can combine information and make inferences.
Yes.
The laws of probability, you know, follow from the kind of thing that Ramsey and Dependencies were proposing.
Yes.
You know, as obscure as they seem, they do lead, if someone is logically consistent, to the laws of probability that allow combinations to be made and things.
Could I ask a question? And it's probably a really stupid one.
No,
I love stupid questions.
no,
Please.
stupid questions
Well,
exist.
Is there like, if you're talking about the way people behave logically, and you're saying, okay, well, the probability of an event is the amount of money that you're willing to bet on something.
Yeah.
Is there not a sort of frequentist thing hidden in that? Because a logical person could potentially say, well, okay, that's the amount of money that I'm prepared to bet, but I don't want to bet because I can't afford to lose it. But
I don't
if I
think-
was to make this bet
Yeah, sorry.
multiple times, so that in the long run I would come out ahead, I will be more likely to make that bet.
I think that's it, Keith. I think, you know, because the frequentist and the sort of Ramsey approach lead to the same mathematics in the end and the same laws of probability, there's got to be an equivalence at some level. So, you know, you can interpret gambling in a frequentist way.
So, but is it, again, you know, sorry, but is it not the case that when you make that definition for this logical person in the one-off betting context, what you're actually appealing to is how they would behave in the long run?
Yeah. I think that if you look at the details of what Ramsey is saying, you know, what the person's trying to do is break even in the long run, at least. So you know, there is an element of that.
But that would be very strange if you are in a way justifying it in that kind of long-term repetition setting when the problem is actually could be a unique one, and the subjective probability is really feasible and can be used for really unique type of situations. If not, it's not really the term or concept that you actually are looking for. I think that this definition that you see here on this slide and the one I referred to from Lindley, they can be used and justified, as I would say, both have a justification in relation to that context, which is rather is unique. There is an argumentation for it that is actually solid for both cases. If you accept the utility kind of framework, you can justify these kind of probabilities, whether it's Finetti or Ramsey or Savage and others. You have some logic in that justification, but I'm just saying that for the practical, for the use in the context of risk assessment, uncertainty assessment, they are problematic. And I'm really challenging the uncertainty environment because it's very seldom I see, maybe probably can discuss this later, that you really are going into this kind of Dennis Lindley part in thinking. It's either no interpretation or it is something of this one, like Finetti and Ramsey and Savage and others. And this is surprising for me. And I'm not having a need to have an answer on that now, but think about it. I often see no interpretation whatsoever on the subjective probabilities. And I struggle with that because if you're going to communicate this, you need to have an interpretation. And then I say, yes, probability alone is not enough. You need to add something. And that also is often missing in my view in relation to the knowledge.
I think that, you know, Ramsey was a philosopher
Yeah.
as much as he was a mathematician. So there was a lot of thought went into his work. And, you know, the aim was to come up with something, as I've said, that leads to the laws of probability. That's not easy. You know, you could come up with all kinds of definitions of a monotone measure of uncertainty, but there's no guarantee that those measures would actually give you a set of coherent mathematical laws. So I think Ramsey agonized over coming up with kind of definition of subjective probability, and it's very, it is obscure, but it works in that it meets his requirement of leading to the rules of probability if the person is logically consistent. So that the only point I wanted to make is
Yeah,
it's
thank you.
arbitrary. I think that's what I'm trying to say.
Hmm.
Okay, great. Well, if there's no more questions, maybe we'll move on to Keith's talk. Last chance.
I will stop.
Okay. Thanks so much again, Terje. Let's thank our
Stop the
speaker.
screen. Yeah, thank you.
Okay, just bear with me a second. So next up, we have our duo of Professor Keith Worden and Professor Scott Ferson on the topic of say what, which I don't think encompasses Keith's title. So maybe he can introduce his talk. And Keith is a theoretical physicist from York University, as a PhD in mechanical engineering from Heriot-Watt Uni. And he's done a period of research at Manchester, and now he's ended up in University of Sheffield, where he's happily remained since. His research is concerned with a variety of different applications, advanced signal processing and machine learning methods to structural dynamics. The primary application is in the aerospace industry, and he's a key partner in the digital twin program. I'm sure all of you are familiar with Scott Ferson as well, our director of the Institute for Risk and Uncertainty at Liverpool, UK. For many years in applied biomathematics in the US, has a PhD in ecology and evolution at Stony Brook. And he's also a central figure in the development of probability bounds analysis, an approach to reliably computing within precisely specified probabilistic models. So I'm very delighted to hand over to them. Keith will be our first speaker. So if you'd like to share your screen. And you currently have your mic muted as well.
Yeah, I'd like to share my screen, but I've got a little bit of an issue. Just give us a second.
No.
I'll not be a second.
Oh no, I think it's doing something. Great.
Have you got that now?
Yeah, we can see that. It's not full screen yet, but it's can see it clearly.
Is that okay?
Perfect. Yeah. Thanks, Keith.
All right. Okay. I'm not somebody who can speak with a great deal of authority about uncertainty, either mathematically or philosophically. So I wanted to try and talk about something that is a concrete issue for me, that is based on the idea of epistemic uncertainty. And so where this comes from is that Scott and I and Robin actually, are all involved in an EPSRC program grant on digital twins. Now, digital twins seem to be all things to all people. If you ask two people what a digital twin is, you'll get three opinions. So I don't really want to talk too much about digital twins because I struggle to understand exactly what I'm talking about when I do that. So what I wanted to do was to pull out something that I could define that would help me understand some of the problems I'm interested in. And so this is basically about an attempt to find a framework for talking about models, because what I'm interested in is what the prediction capability of models is going to be when they're tested in new circumstances, really. I'll elaborate as I go along. Francis, I'd appreciate it if you'd like wave a flag at me at about 17 minutes or something.
Okay, no problem.
So this is just motherhood and apple pie. You know, digital twins have arrived and everybody loves them. But there really isn't any consensus on what a digital twin is. But what I think is inarguable is that because all of these digital twin ideas, at least extend the concept of a computational model, then a computational model must be a core ingredient. And because we have to believe that the model is actually in correspondence with the physical twin, this model has to be validated. But people will use digital twins in situations where they're essentially extrapolating. So the question for me is, can I work out how badly things are going to go wrong if I use a model in a circumstance that it wasn't exactly designed for? And it strikes me that what I would like here is a sort of algebra of models so that I can add substructures together and I can make some statements about how their predictions are likely to succeed or fail. Now, I'm going to frame this in terms of one of the fundamental problems of V&V, verification and validation. From an engineering point of view, I can't claim to be a theoretical physicist any more than I can claim to be an engineer. I'm not altogether sure what I am, but it won't stop me going on about stuff. So, fundamental problems of V&V. From an engineering point of view, what is the lowest cost model that I can use that will make predictions to my required accuracy for the structure I'm interested in the context that I'm interested in, the environment of the structure? And then the next question is, what is the lowest cost program of experimental testing that I can get away with that will validate that model with some confidence? So you can see that when you break it down like this, you don't need a model that represents this whole structure across its whole range of possible behaviors. You only need it to work in your context of interest. I have heard somebody say that a real digital twin, whatever a real digital twin is, represents all of the physics of the structure of interest. And if it doesn't do that, it's not a digital twin. Well, we would digress if we talked about this, but I think that basically says that there are no digital twins, so it's useless. You can think about this in a machine learning context, which is something I tend to do. And then it's about generalization, which is what machine learning people call extrapolation sometimes, but it's not quite. Having learned from some model data, calibrated a model or updated a model, whatever you want to call it, can you say something meaningful with that model about your structure when the structure or the context actually changes? So I didn't want to call these things digital twins because, like I say, nobody agrees what a digital twin is. But I also don't like the idea of a twin being something that's in exact correspondence with something else. If you're suggesting identity between a structure and a model, I don't think that use of the word twins justified by biology. So you can look at the statistics for births of twins, and you can talk about how many are non-identical twins, but I think you really only have to look at this picture to understand that twin as a word doesn't suggest identity. Digression. So I'm going to talk about these things, and I needed a new word, so I'm going to call them mirrors. So a mirror is an instrument that faithfully reflects reality in terms of the parts of the object that are facing the mirror. And so the parts that are facing the mirror, I'm going to formalize in the idea of a context. So now I'm just going to give a shed load of definitions in order to get where I'm trying to get. And I'm going to start with the simplest situation I can think of, which is a completely physics-based model, or what we would call a white box model. And I'll come to database and hybrid models later. So I'm going to assume we've got some structure or system S, and it's the physical object that we're interested in. It has some objective reality, independent of where it is. We can put it in a vacuum if we want. then the changes in the conformation behavior of the structure are going to be summarized in a state vector, which is going to be a vector of measurements that completely characterize the state of the structure. And anybody familiar with state space dynamics is not going to be unhappy with this. And then we need the environment as well, because the structure could be placed in different conditions. So I'm going to call the environment of S another set of environmental variables, another state vector basically that sums up everything that's going on in terms of the environment. And these can be uncontrolled aspects of the environment like the temperature or the humidity, or they can be controlled, they can be a force into the structure. So I'm going to define a context for the structure as being some subset of the variables, okay, which essentially summarizes my problem dynamically. I'm going to be able to measure a certain number of state variables, maybe not everything I need to capture the behavior, but some subset. And I'm going to be able to measure some variables that express the environment. So the subset of the environmental variables is going to be called the environmental context, and the subset is going to be called the response or the predictive context. Now, I'm going to define a schedule for a context to be a set of measurements of the environmental variables over some period of time. This is our data, if you like. If we're thinking in machine learning terms, this is our training data. Yeah. And it's essentially the inputs to the problem. And then I can define a response to that schedule and that context as being what the state variables do when they're presented with that environment. Maybe temperature changes, loading changes, or whatever. And then I'm going to define a test as something that measures the environmental schedule and something that records the response to it. And we can divide this up into training and test data for machine learning purposes. Okay. Now, a model of the structure for a given context is some mathematical function that attempts to predict the behavior of S for a schedule specific to that context. But it has to work for every schedule. It has to generalize across the schedules. And this will be any type of mathematical model or computational model that you're happy with. And a simulation then is feeding some set of environmental variables into the model and getting the model response, which is M now rather than R. Okay. Now, this is just a lot of words really to say we've got a response from the structure and we've got a response from the model. I know. So now we get to the heart of the thing. We need a metric on a given context. And that's going to be an error function, essentially. It's going to be a distance function that I can apply to the model response and the structure response. And so the distance between the model response and the structure response is going to be this object here where I feed the model and the data into some metric and get some number. And now I'm just going to call the model an epsilon mirror if this distance is less than epsilon for all of the possible test schedules in some data set. And then I'm going to say that that model is fit for purpose in a given context if it's an epsilon mirror for that context and the epsilon is less than some critical threshold that an engineer would say satisfies the context requirements. Now, I don't really want to overrun, and I don't want to drown us in a load of definitions, but that is for a white box model. Okay, that is where the model or the object that produces this M function is purely driven by physics. It's a finite element model or a boundary element model, or it could be a CFD model. It could be anything you like, really. But that won't do in our current frame of mind for fitting models, and it won't do for a digital twin, because we might want to refine the model or improve it by using some measured data. And so we need to extend it to Greybox models or hybrid models, which are mixtures of the two. And a Greybox model will have some physical core to it, a white box model, and it'll have some parameters that are adjustable and are fixed by the data. So that's a Greybox model, essentially. And so here, this thing here is a model. It's a hybrid model. It is for a specific context, and it's been trained on a set of training data. Okay. Now, this is a good point to talk about uncertainty, because generally speaking, the training data will be sampled from some distribution. It'll be the result of some experiment we've done. If we'd have done the experiment at a different time, we would have got different results. We'll get different predictions. So the simulation responses from this model are actually stochastic processes. And when we do the simulations, we might try and assemble the whole density function for the responses, or just one response, or just the low order moments, or whatever. But we can still use this idea of an epsilon mirror, because if we can work out what the predictive mean of the process is, then we can use that mean response in that distance function, and we can define an epsilon mirror in the mean. If we've got enough information from the model to build confidence intervals, we can define an alpha mirror, which basically just says that with some specified confidence, it'll make predictions within some distance from the real predictions. And we can use various metrics for comparison in the uncertain case. We can use Kullback-Leibler divergence on these density functions if we can find them, whatever. Now, the problem is that if we raise the question of uncertainty, we've got to rethink what we mean by the environment. Those variables that are not part of the structure, they're part of its where it's situated. And these could be controlled or they could be uncontrolled. We could have forces applied to the structure, or we might have what we call environmental and operational variables in SHM, where we won't know what they are. It's the temperature or the humidity, or if we're talking a bridge, it's the pattern of traffic crossing it or the wind. And so we've got to separate these variables into the controllable and the uncontrollable context. And this is really important if we want to make predictions for the future. Because if we're trying to make a prediction in some previously unseen context, we might still have control of the forcing and know what it is, but we won't know what the uncontrolled environmental variables are. Now, if we want to do the best that we can here, what we need is a generative model of the uncontrolled environmental variables that will make some best estimate of the uncontrolled variables that can then go into our model to make a prediction, right? So we get finally to another object here, which I'm calling a virtualization. And a virtualization for a given context is two models. It's a model of the structure that might be a hybrid, and it's a model of the uncontrolled environmental context. And I'm going to assume that both of these things are epsilon mirrors with some tolerances, because what I want to do is I want to prove theorems eventually about these things. And a virtualization is what you need here for a what-if scenario. So I want to try and give a concrete example now, because we've just got lost in a load of definitions now. Suppose we've got some structure that we're interested in, and we've got some context in which it is used. And we imagine that we've got a virtualization of this, and it's been validated. We have data, and we know that this is an epsilon mirror for the structure in that context. We know we can trust it to some level of predictive capability. So now imagine that you want to design a new structure, and you want to know how it will behave in either in the old context or in the new context, or C dashed. But for economic reasons, you don't want to build or test a full prototype for S dashed. Now, obviously, there is a cost benefit in having some technology that can make these sort of predictions. It's difficult, but it would be a good thing to have. So here's the basic question in this design example, right? We haven't got a direct means of validating the new virtualization. We can modify our finite element model or whatever it is for S and make it into S dashed. And we can still use some aspects of the environmental model, but we might tweak that as well. So here is a theorem, basically, that I'd like to see proved in this context. So let's imagine we've got some virtualization for S, and it's an epsilon mirror. We make some structural modification to S, which changes it into S dashed, in such a way that we know how to make the modification to the models.
Sorry to interrupt, Keith, just letting you know you have your 70 minutes in.
Okay, that's fine. So the question is, if the original virtualization is an epsilon mirror with some tolerance epsilon, is the new virtualization a mirror for the new structure? And if so, what are the smallest epsilons for which it is true? It might be true for massive values of epsilon, in which case this is no use to us. Okay, the prediction bounds are so big it's no use. Okay. Now, at the moment, and this is why I'm doing this talk, at the moment, you might be looking at that and thinking, okay, that is just completely empty formalism. Yeah, you've just made up a lot of definitions. But it's not quite empty yet, because there are circumstances where I think there is technology that will allow us to prove theorems like this under certain restricted circumstances. Okay. And these circumstances are where the data for the prediction for S dashed are drawn from some distribution. We don't know what that distribution is. But what I'm saying is that the uncertainty and what S dash will do is purely aleatory, and it's characterized by some probability distribution. And we assume the same is true for S. Whatever S will do under given circumstances, the uncertainty is aleatory, and the results will be drawn from some distribution. Now, if you make those assumptions, I think the technology to look at problems like this exists within a field of machine learning called transfer learning. And the reason is this: within ordinary machine learning, where you essentially get some data from a system, and you try to work out how badly that model is going to predict with some new data from the same system, you can use technology from statistical learning theory. You can use theorems of Vatnik and Chervonenkis and various other people to try and bound the generalization error. in the case where you have two different structures, which turns it into a transfer learning, I have a source structure and a target structure, I can stretch a point and I can imagine where I can use new generalization bounds that have been proved for transfer learning. So this looks difficult, but it actually looks doable. The really big problem, which is why I'm talking about it, is this. We don't just have aleatory uncertainty to worry about, obviously, okay? When we go from S to S dashed, we might weld two substructures together, and we don't know the physics of the weld. We're almost always going to introduce some epistemic uncertainty when we go from S to S dashed. And I can still ask the same question, but now I can't invoke generalization bounds. Even if I can get them to work in a transfer learning context, because this theory doesn't work for epistemic uncertainty. It isn't built for it. So this talk really is a wish list of huge proportions, really. There's somewhere that I would like to get to, which is a long way away, and there are some big hurdles on the way. The first is putting the framework in place to deal with aleatory uncertainty. And then the bigger problem, in a way, is how to deal with epistemic uncertainty. So, conclusions, really, you know, I've just said what these conclusions are. I've come up with a load of definitions as part of a wish list for some problems I want to solve. I think this is the right framework for asking the questions in, and I've got some rough ideas about how to get answers under restricted circumstances, but not in the general case. And the big problem with the general case for me is the existence of epistemic uncertainty when we're designing and testing structures. So I'm going to shut up at that point.
Great, thank you very much, Keith, for your talk. Scott, do you want to follow on and share your screen? I think you might have to stop sharing your screen, Keith.
Yeah, I was just leaving it up in case we took any questions now, but if we're going to do them all afterwards.
Oh, sorry. Yeah,
no, it's okay.
I think, what would you rather do, Scott? Would you rather have some questions now or at the end?
Yeah, we can have questions now, sure.
Okay, great.
If they're specific.
Does anyone have any points to raise? Of course you can, Vladek.
Yep.
Hi, Vladek.
Hi, how are you? Haven't seen you for a while. Yeah, hopefully you'll still be able to come to El Paso at some point, right?
Well, I hope so, but it's been 20 years.
Yeah. So big question is the following. My kind of understanding is when you require that it's epsilon accurate for all possible cases, that may be a little bit too strong, because usually in machine learning, what they do when they prove these theorems and in statistics in general is that only you are epsilon close with certain probability, and you can have this probability as great to 1 as possible, but aren't you kind of limiting it when you're requiring that it's true for all cases?
Yes, you are, if you want an epsilon mirror, and that's why I've defined alpha mirrors as well.
Okay, okay. But are there epsilon mirrors in real life? Because my understanding is it's kind of, no matter what you do, whether you have a digital twin of, like, I don't know, a plant or something, is it realistic to expect an epsilon mirror, or what's your experience? Again, I'm not a specialist in digital twins, so I'm not.
Right. Well, what I'm going to say here is that this is maths, so we can say anything we like. What reality does is another matter.
Okay. Okay. Yeah, but like Wapnick's bounds, they're all probabilistic.
They are. They
right,
are.
Right. So they're all about alpha kind of mirrors as opposed to epsilon mirrors in this sense.
Yeah, I think so. I think that's where we'll get to. So the Wapnick stuff is beautiful. and restricted in its application to our sort of problems. But there's some beautiful papers by a guy called Ben David in the machine learning literature, where he generalizes these bounds to transfer learning problems. Mm-hmm. And we start to see that we can use that technology. The big problem with these things is the bounds always look like this. They go, error on the testing set is less than or equal to error on the training set plus a term. Mm-hmm. And as far as I know, nobody's looked at whether that term actually gives anything like a sensible value. So 10 is less than or equal plus 1 plus 500 million is not much use to us as engineers. And this is one of the things that I find interesting about this, that nobody's really tested these things in an engineering context. I'm in danger of rabbiting here, and I know Scott has to talk as well.
Sure. Does anyone else have any follow-up questions before we move on to Scott's talk?
I just had a very quick one for Keith. No, thanks for the talk, Keith. It was really, really fascinating. But at the heart of it, I guess, is, epsilon, which is a single scalar measure of the difference between the model and the test data. And, the model can predict stress, acceleration, displacement. There might even be a cost model in there. Is epsilon some kind of utility function in general, do you think, where it's got a built-in judgment of the importance of different levels of agreement?
I think epsilon depends on what your metric is.
Yeah.
Yeah, and the dimensions and the interpretation of epsilon will depend on what your metric is. So the metric could just be like an L2 norm between two sequences of points, but it could be something really complicated that's weighed in all of the consequences of getting the model predictions wrong. Yeah. So it could be a utility, or it could be something else. Yeah. So to allow for the sort of uncertainty that Vladik's talking about as well, it doesn't work to talk about epsilon models probabilistically, maybe, but if you think about the prediction uncertainty in a sort of interval context, and you say, well, epsilon's the upper bound on the error that I'm going to get, you can have an epsilon mirror in that context, but it won't be probabilistic, I don't think. Is that okay, Robin?
Yeah, thanks, Keith. Yeah.
Okay, I think we have another hand raised from Dom.
Yeah, thanks very much, Keith. It's only a very quick comment from me. I don't know if you've come across the NASA challenge, the 2020 NASA UQ challenge. Crespo, who presented, was it the last Vice event, I think? He arranged it. If you've not come across it, the journal will be released in a couple of months' time. I'm not quite sure. The deadline's just passed anyway, so everyone's got their submissions in. But there's a lot of topics that overlap with yours, so it's a problem that's very, very similar. Updating some uncertainty model with a mixture of epistemic and aleatory uncertainties, and using that to inform predictions, and then modifying decisions around these points. I don't know if you've seen it, but
I haven't seen the 2020 one, but we've done some work recently on one of the earlier ones, the one where you've got a beam and then you put a 3 degree of freedom structure on top of it.
Yes, yeah. I think that was the earlier one.
Yeah, so that's one of the things that I would like to use as a test bed for this stuff if I can get it going.
Sure, and I think the air mod one was another one. I don't know if they're related to the two.
We've just built one of those in our lab. So.
Oh, cool. Sick. Yeah, so some of the entries, there was just a conference. It was at, someone will tell me which conference it was at. I'm sure someone will pipe in. But there was just a conference with some of the solutions, and some of them look really interesting, and they might help fill in some of the gaps in your formalism. So it might be worth you having a look over some of them. I don't think go on, sorry.
it's quite funny hearing somebody say, fill in the gaps in your formalism, because it's just gap.
Well, there's some nice slots at least.
There's just one massive slot.
Well, I'm glad you said that, but yeah, it said no one's looked at any machine learning processes, but there's a lot of Bayesian attempts to solve some of these problems, then mixed formalisms, a mixture of uncertainty models and stuff. So it might be of interest. And also, there's quite a lot of work on the different distance metrics in the calibration case, but it might be useful for some of your thinking around the distance metrics for your epsilons.
Yeah, so that's another thing. My colleague Paul Gardner was looking at validation metrics quite closely for a while, and he fed back a lot of interesting stuff to me. I better let Scott talk, because otherwise I'll cause trouble.
Sure, I think we're still good for time, so not to worry. But I mean, Scott does have a lot to get through. Would you like to share your screen, Scott?
Sure. Can see. I'll also
crystal clear.
I'll also try to take myself off. Yeah. Okay. Well, I was tricked into doing this talk by Terje, Aven. I don't know how that happened actually. Let me just set a timer so I can be pretty reasonable. I'll just say some outrageous things and see if anybody bites, and we can have an argument about it. That will be my plan. So I think that we're at a crossroads in talking about uncertainty, the theories of uncertainty. And what I want to say is that there exists some kinds of uncertainty that can't be handled by traditional methods, by traditional probability in particular. And what we're seeing is a collision of different views about uncertainty. In fact, I apologize to anybody who's ever heard me talk ever before, because I'm going to say exactly the same things. And in fact, you've heard this talk already in this series, sort of, because Daniel Straub talked several days ago. And if you just put a not in every sentence of his that didn't have a not, and also take out a not in any sentence of his that did have a not, then you will have heard my talk. So it is a collision for sure of different views. And I think that what's going to come out on the other side is a larger theory, a more complete theory that has wider applications, and it can address more real problems that are in a reasonable and more reliable way. Right. So we have a problem in engineering, and that is things keep failing. Of course, they've always failed, but they've been failing kind of more dramatically, seemingly lately, and also failing within spec, in the sense that, you know, we thought we had done the risk assessment, but somehow the thing that came out was sort of way outside what that risk assessment said. So Fukushima, for instance, and the Deepwater Horizon spill, certainly the Columbia disaster, that's the Minneapolis bridge collapse in 2007, and also that same year and into the following year, the financial crisis, which took out the Northern Rock Bank here in the UK, and it was the first time that the UK had a bank failure of this kind, because people literally made a run on the bank, and it was the first such failure in 150 years. What's going on? And this is not the only list. I mean, Bill Oberkamp had a similar list of what I'm calling dramatic technocratic failures, right? So the shuttle risk was originally estimated by NASA risk analysts to have a risk of the loss of the vehicle and crew to be about 1 in 100,000 per flight. Well, you know, there were 2 losses. So it turns out there was actually like 1 in 70 flights is the true risk. The financial disaster of a few years ago was caused by grossly understating those financial risks. And in the United States, at least, and I think also here in Britain, people who are in charge of estimating flood risks are not doing a good job. We're having 100-year floods more often than we should be having them. And people don't get the message. We're flubbing the risk communications as well. And you don't have to live in Texas to know that failure cascades in electricity distribution systems are more common than they're forecasted to be. It's really annoying. And there's a long list that goes on and on of different things. About that Minneapolis bridge collapse, I knew something was amiss when a famous engineer said of the collapse that it was a 1 in a billion event, which just tells me that engineers don't know what the word billion means. So I would like to say that it seems like these are not noble failures. These are not things that we knew the risk and we took the risk, and yes, we were bitten by the risk, but it was a risk that we had under control. It's not that. These are occurring more often than our risk estimates predict, and the managers don't see the problems that are coming around the bend. And I think that it's clear that analysts are doing the risk estimation wrong. All right, so that's my outrageous statement, and here's what I think we're doing wrong. It's a short list of things that we're doing wrong. Everybody's easy, the whipping boy is uniform distributions, of course, the inappropriate use of uniform distributions, but it's also unjustified independence assumptions or overly precise dependence assumptions, other kinds of more general assumptions of equitable probability, assumptions of stationarity that are misplaced, treating epistemic uncertainty as though it were aleatory, not accounting for model form uncertainty or ignoring uncertainties in the input data, modeling choices as though they're random, and using aggregation or using averaging, sorry, as a form of aggregation. Of course, the general problem is that we're just engaged in wishful thinking. We would like our problem to conform with our analysis, the analysis that's easy to do and is mathematically convenient. Of course, the real world doesn't usually line up in those convenient terms, and so we end up making assumptions that are really not true and getting improperly structured results as a consequence. Okay, so these mistakes also compound. The errors work in the same direction, to underestimate the risks. And that seems to be systematically compounded through all of the kinds of mistakes that I listed on the previous slide. And of course, omitting uncertainties would likewise lead to understating risks. And more to the point, that using traditional probabilistic methods often forces analysts to make assumptions that understate these tail risks. That's the main problem. So now you're familiar from these previous talks about the two kinds of uncertainty, and of course they have many different names. My favorite, of course, is type A uncertainty and type B uncertainty, because those are so mnemonic and explanatory. I think those are the best names, perhaps. But I call them, just variability and incertitude. You can call them whatever you like. I don't think it's the case, as Daniel argued, that you can't tell them apart, though. Now, source, if you change the context, then one can turn into another, that's for sure. And sometimes their distinction can be subtle, sometimes even like dividing ice from snow. But I think it's essential to divide ice from snow, because getting hit with a snowball is really very different from getting hit with a block of ice. And our engineering assessments will differ greatly depending on how we treat these two kinds of uncertainty. All right, so you know the two kinds, right? Aleatory uncertainty or variability just comes from the wiggliness of the world, spatial variation, temporal fluctuations, manufacturing component differences. It's not reducible if you study the problem further. If you take more samples, you just get more variation, not less uncertainty. In contrast, of course, incertitude or this epistemic uncertainty comes from just not knowing very much. It's limited sample sizes, or having small, or having poor measurement quality, poor measurement uncertainty, or using the wrong kind of thing to measure in. And it's reducible. If you studied the problem more, invested more effort, you could theoretically reduce the uncertainty or the epistemic uncertainty. All right, so let me talk about three kind of simple examples that I think have not been properly addressed by the folks who think that probability is sufficient to do assessments. These are simple problems. I don't think they're simplistic problems, because you see these problems arise in that and that's the assessments that we do. So this is my famous open problem. I ask this all the time. Suppose A is between 2 and 4, and B is between 3 and 5. And I ask, what can be said about the sum A plus B? And usually, depending on the room, I get between 50% and 95% of people saying that it's one way. So what do the probabilists say? I don't think this is a straw man. What they say is, literally, they say A has uncertainty between 2 and 4. You should model that with a uniform distribution, and likewise B. So when you slam two uniform distributions together in some spreadsheet or some simulation program, the distribution that you get out for the sum is a triangular distribution, right? It says that the chance that it's 5 is vanishingly small because it has to have A be 2 and B be exactly 3, and that's vanishingly small, right? I think it's clear that that's the wrong answer. The right answer, of course, from a risk analyst's perspective, or perhaps from an engineer's perspective, is no, it's the range, not the triangular distribution over that range that matters. Because who said that A couldn't be 2 or B couldn't be 3? I said that they were in the range. Why wouldn't they be allowed? But probabilists over and over again, even when I phrase the question in these stark terms, they all say, well, some of them say this is an illegal question. You're not allowed to ask this question because it never would be the case that I would only have that sort of information about A and B, right? As if, forensic timelines never looked like this. Right? It's perfectly clear they look like this all the time. In fact, in discussions with Tony O'Hagan, I had to make a list of all the kinds, all the times that these kinds of incertitude come up. They come from periodic inspections. They come from plus or minus measurements or limited digital readouts from non-detects, data censoring, privacy, a whole bunch of reasons that we could have this kind of incertitude. So I don't think that's somehow specious or somehow not realistic to say that we experience uncertainties like this. And I would like to argue with Tony and Daniel and others that not only is it important to distinguish between these two kinds of uncertainty, but it's really important to treat them differently, because variability or aleatory uncertainty should be modeled like randomness, because that's what it is, and we should use the methods of probability theory to do that. And in contrast, incertitude or epistemic uncertainty should be modeled like ignorance, because that's what it is. And we should be using the methods, if not of interval analysis, at least more generally constraint analysis. And my brethren and sistren, I don't know what that, my fellow travelers, believe that imprecise probabilities and maybe computationally probability bounding can do both at once. It can do both of these kinds of treatments for these two kinds of uncertainty. All right, so this slide was originally given at that meeting that Terje Aven mentioned in Los Angeles. So simmer down. I'm not saying that we should just use intervals. Nobody said anything like that. And I'm not saying that all uncertainty is incertitude either. Clearly, that's not true. And I'm not even saying that most uncertainty is incertitude. I don't even think there aren't situations in which the incertitude is entirely negligible. That's great, good on you. If you're so lucky as for that to happen, that's wonderful. And if that's the case, then probability theory is perfectly sufficient for your analysis, right? But what I am saying is that some analysts face what can be described as non-negligible incertitude. And handling it with these standard methods requires assumptions that really may not be tenable, either uniformity or unbiasedness or independence or some other sort of assumption that really isn't justifiable by what we know. And in that context, we have a problem, right? It'd be useful to know what difference relaxing some of these untenable assumptions might make. And that fact can be discovered by bounding probabilities in some way. All right, so that same problem, that same open question problem, when it's iterated, it becomes more stark, I think. If you have a few grossly uncertain inputs that you characterize by uniform distributions, well, according to Laplace and all his followers, all the way down to Daniel Straub, I think, he would say, well, use uniforms for all of these variables that we don't understand, and if we're going to add them together, that's going to create, via the central limit theorem, some congestion in the middle, some concentration of mass in that center of the distribution, right? And if there are a few grossly uncertain inputs, that's what you'll get. If you have a lot of grossly uncertain inputs, well, you'll get a whole lot of concentration. In other words, the answer that you get will be a spike almost, it'll be normal in shape, by the way, but it'll be almost a spike. If you look at the CV or the variance as a function of the range, it'll be a spike. And my question is, where does that surety come from? Because you said you had grossly uncertain inputs. You had a whole bunch of things that you had no idea about what their real values were, but yet when you added them up, you have this amazing specificity. The question is, what justifies that? The short answer, no one here will probably be surprised to hear me say, is that nothing justifies that. It's a mistake. It creates what you can call smoke and mirrors certainty. It's the probability that makes certainty out of nothing, because fundamentally, probability theory has an inadequate model of ignorance. It's not doing it correctly. In contrast, IP, the imprecise probabilities approach, gives you a vacuous answer if all you give it are vacuous inputs. That's what should happen. And that's not what probability does, right? So that's the first simplest example. There's a second example. I think you've heard some of this before from Ryan Martin's talk in this series about the satellites in orbit. There are 2,000 some odd satellites in orbit. Half of those are from the US. And they have generated a great deal of space debris, old satellites, rocket stages, hardware that's floating around up there, prior collision fragments, paint and insulation and so forth. The military tracks this stuff. Anything larger than 5 centimeters, they're tracking, and they're trying to get finer detail as well, but they don't quite have that capacity yet. In fact, it's not just 2,000, it's going to be 10, over the next 10 years, it's going to be 1,000 more of these objects in space flying around at very high speeds. And turns out bad stuff happens up there, and it's quite messy. And we had our first hypervelocity collision of satellites in 2009 when the Cosmos 2251 collided with the Iridium 33. The collision was at 42,000 kilometers per hour, and it created a shower of items, they're called, that basically were flying around at these hypervelocity speeds, shredding everything that got in their way. The ISS had to perform an avoidance maneuver to get out of the way of that debris field in 2011, and there are still, most of the items were still in orbit. The big items are still in orbit in 2016. So here's just because they're amazing pictures. Here's the point of collision. It happened over, I guess, Siberia there, and going really fast. And then 20 minutes after the collision, the debris fields were still going around the planet. Here's 50 minutes after the collision. They're re-intersecting, I guess, shredding themselves again. Here's 3 hours later. This is amazing graphics from AGI, who I don't know if they're part of the military industrial complex, but the graphics are like really cool. And you can see that they've basically, these debris fields are encircling the Earth as sort of two antipodal halos now. Okay, if you look at all the 2,000 satellites that are in orbit, well, in general, the debris fields that we have include those satellites, but also bits of previous satellites. If you look at all the stuff that's up there, it's quite a job to untangle or keep track of it all. You can sort of see here the geosynchronous orbit, that big ellipse there. And you can also see the low Earth orbit satellites, which are just like the shroud around the planet. So they're sort of everywhere, right? And of course, you're aware, I imagine, of Kessler's syndrome, in which you have a collisional cascade. So you have debris screwing up one satellite and shredding that satellite, and that creates more debris, which increases the probability of further collisions. And that's going to create, of course, a domino effect with runaway feedback, potentially, rendering space unnavigable for decades. That means no space travel. It also means no satellites. So it means no GPSs and maybe highly constricted satellite communications as well. So cell phones. It would be a big, big deal. It's really got her very upset on the whole matter. the people in charge of tracking these objects are watching. They're doing conjunction analysis. They use positions and velocities and physical models to estimate the probability of collision. If those probabilities are low, then we're good. But if they're high, then you have to move the International Space Station, or move the satellite or something, which is expensive to do, as you can imagine. So what do? Well, the three-dimensional analysis is reduced to two, and then they model the distance from the satellite of interest that they're protecting from some object that might be in its path, and they model that as some norm of some distance x. The true distance less than the radius of the object is a collision, and you derive the collision radius from the size of the objects. Right, so to compute the probability of avoidance, you've got theta, a Bayesian theta estimate to be the difference between the true positions estimated by bivariate normal distribution with known covariance, flat prior for the true distance. Collision events look like that, and the measurement error variance is sigma, what we can measure, and the probability of collision is computed as a function of this sigma. How precise are our measurements can tell us how likely the probability of avoidance would be. So, and when sigma is high, the probability of avoidance is going to be high too, and that turns out to be true for any x. Well, of course, sigma is always pretty high. This is space we're talking about. The space is vast. It's hard. There's a lot of uncertainty about these measurements. They're going very high speeds for one thing, and it's a giant place we're talking about. So the sigmas are quite high. So what happens when we do these calculations? I think Ryan alluded to this if they didn't even show this picture. But if you plot safety as a function of the measurement error, it turns out that if you increase the measurement error, objects seem to be safer. The non-collision probability goes up, including the probabilities, even if the data is showing that they're on a collision course. So these things, which are closer than one radius, or is it one radius or one diameter? I don't know. But they're close enough to hit one another. At least that's what the data are suggesting. But the probability, nevertheless, gets very high of avoiding. And what's happening? The large error in measurement says that the probability of non-collision is high, no matter what the data says, even if they're coming straight at each other. And this is the what and the say what, I think. The available data, may not be great for predicting, and the additivity makes the probability go somewhere. And if it goes to avoidance, as it does in this case, whatever the data, that means that even if the satellite on a direct collision course, the probability tells us it's safe. And Ryan noted that this is an instance of what we call false confidence. The false confidence is the hypothesis getting mass even though the data doesn't support it. And false confidence really is a feature of probability theory. Every additive belief measure has the false confidence problem. There's always falsehoods that are given high posterior probability, just the way it has to work. But that's bad if you're using the plausibility of hypotheses, if you're judging those plausibilities of different hypotheses by the probability magnitude that gets assigned to them. So if you're doing like, BIC, or if you're doing Bayesian model averaging, if you're thinking in that way, then you're going to be led into some problems. Now, the theorems about false confidence don't say where the hypotheses that are problematic are going to be, and Bayesian analysis is usually good for some situations. It's just not good for all situations. But under an IP approach, we can fashion, inference procedures that are well behaved, that don't have this false confidence. So that's the second example of where probability sort of leads us into misleading or mistaken impressions in an engineering context. The third example, and I see I have 5 minutes I only have 30 more slides, so that'll be no problem, right? The third problem is dependence. Of course, in practice, most variables are assumed to be independent of each other. And of course, that's ridiculous. There are clearly variables that aren't independent of one another, including chain delivery systems like, the United States transmission grid. they depend on each other, so they're certainly not independent. And I'll show you just briefly a schematic of the risk analysis, the financial risk analyses that was undertaken for the mortgage-backed securities that failed in the 2007 and 8. This was the highly technical analysis that was done at the time. Okay. Another highly technical analysis we could do on Vesely's pressurized tank. This is, you'll note the pressure tank down here. It has no relief valve, so it's in a nuclear power plant presumably. And then we asked the question: what's the chance that the tank ruptures under pressure, under pumping? Sorry. So here's the Boolean expression involved and the fault tree, and these are some of the numbers that go into that Boolean expression for evaluation. And then we had questions about the dependency. Okay. It says I'm done. I knew this was a mistake. Stop that. Sorry, that was the clown portion of the presentation. What I wanted to say is that we had four different models of dependency. The first case, we just assumed everything was independent, which is the traditional thing to do and what Vesely did. Then the second case, we mixed it up a little bit. We put some dependencies in between some of the terms. So here we said that the S switch was dependent and had a known correlation coefficient with these other systems. And this we said these two things were perfectly correlated, positively correlated. And this we said, well, we didn't know what the correlation was between this guy and these. We just let it vary among all possible dependencies. And then in this case, we additionally said this thing has, we have no idea what this dependence is, and we wanted to relax that assumption. And then finally, we used no dependence assumptions at all. So everything, I guess the vertical lines mean that they're independent, and these other things mean various other things. So we can relax all the dependence assumptions and make no assumptions at all about dependence. And what we get is, in the result of the probability of the tank rupturing is, well, when we assume everything's independent, we get this. And when we had that mixed dependency model, we got this. When we relax that one dependence between the pressure switch S and these components, then we got uncertainty about the probability ranging between here and here. And when we made no assumptions at all about dependence among any of the components, we got the variation in uncertainty ranging between here and here. So what we see is that several things. We see that although you make no assumptions at all, you still get quantitatively interesting and useful results. And sometimes the dependence is very important, like it is here, and sometimes it makes no difference at all, like it is here. Okay. All right, so to conclude, I want to say that your work, if you studied mathematics, you know, or geometry rather, you know that the answer to this question, given a line in a plane, how many parallel lines can be drawn through a point that's not on the line, right? So how many lines can I draw through this point that are parallel to this line? Right? The answer, for 20 centuries, the answer was 1. But about 150 years ago, close to 200 years ago now almost, they decided to relax the 5th axiom and say, ooh, actually the answer could be 0 if you're on a sphere, or many if you're on a hyperbola. And at first, this idea of non-Euclidean geometry was extremely controversial. And these mathematicians were ridiculed to be discussing it. But it turns out that relaxing that one axiom led to richer mathematics and wider applications. And of course, non-Euclidean geometry has been used by Einstein in general relativity. So it turns out it was useful. And I would like to point out that the difference between probability theory and what we're calling IP, probability boxes or imprecise probabilities or almost anything that's else on that scale, is basically the result of relaxing one of those axioms of decision theory, right? It's that axiom that we can rank any two gambles, right? So which value of A or B is more to the right? Well, we don't really know because they overlap. Which value between C and D is more to the right? We don't really know. Clearly they may not be the same, and it's not clear that C is less than or bigger than D. Some of these gambles are really incomparable. If you just admit that that's possible, then you get IP. The result is you get IP. You get richer mathematics, a wider variety of applications, and more realistic models. So the comparison between IP and a traditional Bayesian approach is actually pretty favorable, because IP is still fully rational in a Bayesian sense, except that agents aren't forced to either buy or sell any offered gamble. And the difference is that in IP, you can characterize the max buying price and the min selling price, which might be different from one another, right? In Bayesian terms, those two things have to be identical. Of course, if you know all the probabilities and utilities exactly, then IP reduces to Bayes and everything's back to where it was. But there is such a thing as uncertainty about probability if you allow this sort of difference between max buying price and min selling price. And I should point out that if you're doing a Bayesian sensitivity analysis, then you're essentially already working in IP. You're already in IP. You just haven't sort of realized it yet. You lose nothing to go to IP. It's a pure generalization of probability theory. It's consistent with the Kolmogorov axioms. It can be coherent and avoid shear loss. It just adds more flexibility to your armamentarium. And you can still make any assumptions you want. You just don't have to make assumptions to get results. It doesn't replace probability theory any more than Euclidean geometry got replaced by non-Euclidean geometry. And, can the uncertainty swamp the answer? Absolutely, sure it can. If the uncertainty is huge, it should swamp the answer. It's not unhelpful to admit that you don't know. And if you think those bounds are too wide, then put in the missing information into the analysis and show the contraction, right? If you don't, if there is no such information, then what justifies your belief that the bounds are too wide? And I would ask, who are you trying to fool? Okay, so that's the conclusion. I guess, Francis, we're ready for, that was 50 slides in 20 or 33 minutes. That's not so bad, right?
That's pretty good going, I think.
Yeah. Did anyone cry, or is it just me?
Cry?
No, it was just you, and that's why you turned off the video, right?
I should never stop that timer because I can never figure out how to turn it off.
I got a few people messaging me saying they wanted to see your face whilst you were talking, in fact. Does anyone have any questions for Scott before we move on to the open discussion? I see Vladik is on the end of his seat.
Yeah. Okay. So actually, I have two comments, which kind of may lead to questions. One, it's very interesting that you mentioned this non-Euclidean geometry as an analogy, because of course, it's not clear because Gauss did not leave us exactly, but looks like, based on what some historians of mathematics think, non-Euclidean geometry was the origin of Gauss distribution. Supposedly, it went like that because Gauss was always interested in this fifth Euclid's postulate, whether there is only one line or not and how to prove it. And so because he was a physicist as well, actually the unit of magnetic field is named after Gauss, he decided to make an experiment. So he lived in Germany, so he went to the nearest three mountains, put the theodolites on the three mountains and measured the angles. And when he added them up, of course, he didn't get 180 degrees. But he was smart enough to realize that so he needs to repeat this experiment. So he repeated it several times and he got the bell-shaped curve. And that was the reason why he started thinking of this Gaussian distribution and everything.
Oh, amazing.
Well, again, this is not completely 100% confident because as everybody knows probably, or those who know, that Gauss did not publish anything in non-Euclidean geometry. And it was only when he died, and he was like king of mathematics. So everybody was taking every sheet of paper that he wrote on with awe. Then they found a whole folder called non-Euclidean geometry. because before that it was considered to be not just controversial, it was considered to be a complete nonsense.
Right.
For example, Lobachevsky, the Russian guy who kind of published the book, he did a very smart trick. He couldn't publish it. So what he did is he started writing to the newspapers in Moscow saying how good is the Tsar. And honestly, intelligentsia never likes the rulers. In the US, we can see that. It could be Trump, it could be Obama. Everybody criticizes the government. And suddenly there is somebody who writes how good the Tsar is. So when the vacancy appeared of the president of Kazan University, the Tsar requested very strongly that Lobachevsky be the president. And since he was the president, he published in his publishing house on the government expense his book on non-Euclidean geometry. And all the liberal newspapers had a field day saying how idiots are our rulers because they appoint people who say that geometry could be non-Euclidean. Ha, 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 ha. We definitely need democracy. We definitely need to overthrow the existing government. And only after Gauss died, it became things. Yeah, but the serious comment is that I wanted to add one comment to your listing of why we need to go beyond its tolerance. Because in manufacturing, when you require something to the manufacturing plant, it's usually in terms of tolerance. And when some big stick comes made of metal to the construction site, there is no probabilities guaranteed. The only thing that they guarantee is the length is whatever, 260 millimeters plus minus 5, whatever it is. And that's a very important part of interval uncertainty. Same thing with, for example, electronic parts and everything. Yeah, thanks.
So that's an avenue where incertitude emerges.
Yes.
Yeah. Okay, I understand.
Yep.
Hi, I had a question, Bill Overcamp.
Hey, Bill.
Hi, Scott. Very, very nice talk. It's nice to see you, Scott.
I don't really exist. I'm just a pure energy right now.
No, it's really, really great to see you. I in the first part of your talk, you had some very not only insightful but very deep issues on why don't risk analysts, or you could say organizations or people, better understand the risk. I think it's actually a very deeply human problem. I think it is an issue that has to do with, as Nassim Taleb says, who has skin in the game? And I think that's a very good expression, because let's take the issue of risk analysts. They typically don't have skin in the game, real skin in the game. They may have reputations, but they really don't have real skin in the game. And on this issue of the satellite conjunction analysis, who has skin in the game? I don't think the risk analysts and the organizations, I don't think there's any real skin in the game, because these are big bureaucracies. And if it really does decay into this Kessler syndrome, who's going to be held accountable? I think they'll say, oh, it was a fluke, just like the bridge disaster, or just like the 737 MAX disaster. No, these are not flukes. No, the question of accountability is there. So if you say who actually in a real risk analysis, who has real accountability? It is really the insurance companies. They pay if there's an accident and this sort of thing. And so I think they have shown more interest in this, whereas opposed to risk analysts, they're not the ones who's paying the losses. So I think there is more willingness to embrace imprecise probability in these, because they are the ones that really have the real skin in the game. Other organizations, I really don't see that. So that's an opinion on this. I think this, as I said at the beginning, this is really a very deeply rooted issue on who is accountable for their risk analysis or their decisions.
So I certainly understand that risk analysts need to be getting their funding from Lloyd's Register and Omaha Mutual of Omaha and this sort of thing. But your first point about not having skin in the game, certainly they do have some skin in the game. It's just the different skin. I mean, they're appealing to somebody. I mean, when there was a risk assessment that came up with that 1 in 100,000 flights, right? Who were those people and why did they say those things? Well, we could ask the same question less dramatically about the financial calculations that went on. People will tell you that know about that community that they do these financial risk calculations really as sort of this exercise. They're forced to do something, and so they do this thing. They don't really believe it there because it's, the manager makes decisions not based on the risk analysis. They do it because of their they've got a gut instinct, they've got a hunch about something, they'll do it that way, the same way they've been doing it forever. Essentially, risk analysts are spinning our wheels. We're not really contributing to any decision making in the real world, at least not yet. And I think probably the reason is that old joke about when you ask a risk analyst what the risk is, she closes the blinds, shuts the door, and talks to you in soft voice and says, "What do you want it to be?" That's sort of where we are at this point.
Yeah, one last comment, and I know other people want to ask questions on the shuttle risk loss. That is absolutely a documented quote on what the loss was, what potential loss rate. And as you said, it turned out, and then there's a really nice paper that was published about 3 or 4 years ago. It was in hindsight, what was the risk based on individual knowledge in hindsight? And the risk on the early flights actually went down to like 1 in 10. It was unbelievable. This was a NASA paid for analysis in hindsight. So that's the kind of distortion in risk that has happened. The list you put up, the list I put up a month or so ago, these are not imaginary things. No, these were claimed by people. And the risk analysis in the NASA, I say there was no accountability on there. How were those people held accountable? The same kind of thing in the collapse of 2008. What kind of accountability there? No, there's no accountability in that. So I think that whole issue of lack of accountability is a very deep human issue. And I don't know how you fix it. I'm not claiming that. I'm just wanted to bring out the point that the insurers, they actually have the real accountability because they have to, at least they're obligated to pay. And if there's a massive collision and a Kessler syndrome in orbit, I'm curious what kind of insurance will be paid on that. So thanks for your talk, Scott. Always enjoyable.
Thanks.
Can I add a little bit to Bill? Bill, again, nice seeing you again in person. So sometimes it's vicious because I remember, like in measurement in metrology, there is always a fight between those who want it to be uniform distribution and want to have it as an interval. And like ISO has a standard that it should be uniform distribution. And my former boss in Russia, he went to these meetings and it was like blood flowing out because on the one hand, there were researchers. On the other hand, there were companies who produce measuring instruments and they want to minimize the risk because that will enable them to kind of better compete and sell better things. So it's sometimes, indeed, it's not just people who are not interested. It's like people who are really biased by their economic kind of interests. So I think Bill is absolutely right.
So which were which? The
researchers were willing to have broader things because they want true answers, while the companies who are actually paying for these standards, they want to calibrate it as narrow as possible. So if you have if you have uniform distribution for each component of the error, and you add them up together, the result is shrinking, just like with 2008 banking collapse. If you assume that everything is uniform, you get a normal distribution, and you conclude that something that is deviations that is higher than 3 sigma are impossible.
Right.
And so therefore collapses are impossible. Yes, absolutely.
So Francis, you're muted, I think.
Interrupt. Sorry. I'm just going to interrupt here and move on as a segue into our open discussion, which I think it's turning into anyway. So just a reminder not to bite Scott's head off, and neither Kevin nor Terje's, and have a nice friendly debate around, can we agree on anything about handling epistemic uncertainty in engineering? And everyone feel free to chip in. I think Dominic wanted to ask a question,
Francis,
so maybe it's related, you can say
Francis,
something.
Francis, can you add me also, Aven, because I couldn't find the hand. Couldn't find the hand. So please, I would like to comment on that if you allow me.
Yeah, of course, definitely. You can start.
I can start. Okay, so it was really nice to listen to you, Scott, and I was reflecting on what you were saying and comparing our early discussions and what I was saying, and I think that you are saying that there is absolutely a need for seeing beyond precise probabilities in relation to uncertainty assessments, and I agree. We agree on that for sure. And you, in a way, advocating, arguing for imprecise probabilities as the key instrument in relation to that, if I'm right. And I think that this kind of conclusion that you need to see beyond probability and let's say traditional probabilistic analysis, as we have seen in the 80s and 90s and so forth, a lot of, I say, several schools have been on the same line. I mean, think about safety science in relation to resilience-based thinking. Think about post-normal science. Think about also, say, modern risk science is all in agreeing that we need to do that. The question is actually how to do it. And I personally think it's not enough to think only in relation to imprecise probabilities, but it absolutely is a key instrument in relation to that uncertainty. Also probability bounds is fine, but I like to see a broader package than these two. That's my view. And otherwise, I am fully on line with what you're saying, except for one little thing then, Scott. This for fun, I mean, with a smile, you know, this Frank Knight thinking about risk as aleatory uncertainty or just simply a chance, or, you know, this kind of uncertainty of type 1 A. This is not the way we're talking about risk today. It's sort of outdated, because that would be a very small little risk world if that was the interpretation of risk. Risk is really capturing uncertainty. Otherwise, it would not be in line with common ways of using that term. Thank you.
I'm not sure that needs a response, but I guess I would ask the question. I was probably futzing with my slides when you were talking, but I know that there are multiple kinds, right? So what are the kinds that you want to say? There's the imprecision, there's the aleatory, which you distinguish, right? And what's the third, or how many are there?
Well, you were listening to my talk, and I mean, in relation to uncertainty assessment, I still argue, and I think you agree, that probability exact is a useful tool.
Yeah.
Imprecise probabilities is a useful tool.
Yeah.
And in addition, which I don't see is not referred to, I think that you have to include the knowledge supporting and judgment about that, how strong that is.
So that's subjective, what you would call
probabilities, yes, and also in relation to imprecise probabilities, because that imprecise probability could have been developed based on a rather poor knowledge, and that need to be reflected.
So does that mean there are 4 things then? So IP, probability and IP, and
Yes.
subjective and not subjective, I guess. So there are 4 elements.
Yeah.
Okay.
Yes.
Okay.
But I really think in relation to the way you are characterizing the uncertainties using a measure, exact or imprecise, and then you have actually, so depending on how you are sort of labeling these concepts. Thank you.
Dominic?
Yeah, can you hear me? I think yes.
Yeah.
So I kind of want to follow up on Bill Oberkampf here, because, and maybe this is also asking about the connection between your talk and Keith's talk. So for me, probability, like any uncertainty measure should still be treated as a model, and like we as scientists should be able to, in some sort, validate these models. So what does it actually mean if something that was predicted to have a probability of 1 in a billion or whatever, like, and now it happens? What does that mean for the model? Like, is it invalid or something? So, and we can have lots of arguments about what's the right way to model this, but I think that going from the tail here, or what, I don't know how you say that you should actually judge whatever uncertainty measure you're having by the quality of the predictions, right? Maybe you can comment on that, or yeah,
well,
I don't know.
I think that's clearly extraordinarily important. And I mean, there was a lot of discussion earlier about Ramsey and about Definetti. Everybody knows that Definetti was the champion of the betting definition of probability. But I think few people, and I guess Matthias isn't here so to mention it, but few people seem to know that actually Definetti abandoned this definition in his later career. He realized that this betting definition of probability could be gained, or would be gained, and therefore wasn't a good measure of probability. It wasn't a good definition of probability. He ended up with what we use now, which is this Breyer-Score style thing, which is much more reasonable if you're talking about validation situations. I agree that uncertainty characterizations should be considered models, and they should be subject to verification and validation. And that means data. And it means checking the inferential methods for performance. Right now, we sort of don't do that. We use methods because they're convenient. We use methods because we're told that they create rational results. But that's not really a good enough reason, it seems to me. You can have rational results that are completely wrong. They're internally consistent, but they're just empirically wrong. And we see that all the time. If I balance my checkbook, and I'm very consistent about how I balance my checkbook, but it doesn't agree with the bank, it's not the bank that's going to suffer in that situation. It will be me. If I'm not paying attention to empirical reality, it seems to me we're not doing the right thing. So I agree completely, obviously. And I assume everybody else agrees too.
Well, I'm not agreeing on that.
Okay.
If I allow, because it's I mean, if at least in the risk assessment world, I mean, if you are thinking about that, the accuracy of predictions is the way to think in relation to quality. I mean, in the NASA example, it's certainly failed, because if it's a rare event type of issues, risk assessment will not ever be able to deliver accurate estimates or predictions. So I think that you need to have a broader way of looking into risk assessment, uncertainty assessment, as in a way of characterizing what you know and what you don't know type of attitude, compared to having this kind of accurate prediction as the goal, because then you will certainly fail, and risk science would not be, or risk assessment would not be working. I mean, it will fail, certainly, because if the uncertainties are large, you will never be able to do that in an accurate way.
So because risk analysis is dealing in the land of bad data, right? Effectively, you don't have the chance to validate, but you can validate the methods that you use.
Yes,
right?
yes.
And maybe that's the minimum that we would aspire to then.
Yes, and there are certain rules you should follow. I agree. The kind of approach is subject to this kind of validation.
Sure.
Yes.
Keith has a hand.
It's just a remark, really. It sort of relates to what Bill was saying about pre and post assessment of probabilities, and how people look at things. And it reminded me of, like, 20 years ago, I was talking to the ex-wife, and she was telling me that one of her friends at work had a baby girl. And I was saying, yeah, that's nice. And she said, yeah, the last 20 babies of work have been girls. And I said, wow, really? I said, the chances of that are over 1 in a million. And she looked at me and said, don't be stupid, it happened. So
I'm not sure. Is there a message from that story? I mean, I'm not sure that's the same.
That is the message, though, isn't it? That is the message. She is much smarter about the use of probabilities than basically any risk analyst in the world.
Well, on that, I watched a YouTube video a little while back, and it was talking about whether or not somebody cheated at a video game. But as part of the analysis, as it were, the guy who was doing the video looked and went, okay, what's the most lucky that people have been in casinos in terms of, that video that Joshua's put up. And essentially the point was that there have been documented cases of people in casinos who have managed to get roulette wheels for 30 in a row, which works out as like 1 in a billion or 10 to the 9-esque probabilities. And
I would still look at the croupier, wouldn't you?
Well, there's that, but you would think that a casino is likely to be the truest sense of probability. And it's they're going, okay, so things that are 10 to the -9 happen, and we have documented evidence of it. So if you look at these disasters, well, if your chances are that if there is a problem, if that happens, maybe we should start worrying about them.
So, I mean, you should unmute yourselves and just start speaking, I think.
Scott, yeah. I wanted to add a point that Professor Aven made about risk analysis and the difference between risk analysis and UQ, or you could say the dependency of risk analysis on UQ. Uncertainty quantification, as you point out, is much broader than just probability. There's, of course, ignorance, and how do you represent that? And do you have the flexibility to represent it with intervals as opposed to uniform distributions? And as you mentioned, and I also mentioned in my talk, if the only assignment you can give is a distribution, and as I mentioned, an interval wrecks the machinery in traditional probability, you can't do that because you can't produce a result. So you put the least informative that you can, and that's the uniform distribution. And so that weakness in uncertainty estimation, given traditional probability, as you point out, that is a very clear weakness, and Vladek has pointed it out in many different ways also. But one of the things that you haven't mentioned here, and it really wasn't appropriate, but that should be mentioned, is the other factor, and we usually take the product of consequence, negative consequence of event, and probability as the risk. There is also massive uncertainty, ignorance, epistemic uncertainty in the negative consequence of the event. That has traditionally not been recognized. And when I review the, let's say over the last 10 years or so, the risk assessment community, at least in my view, is better recognizing that both of those potentially have very large epistemic uncertainty. It's not just in the UQ, probability side, but it's also in the negative consequence side. Let me give two examples. One of them is 3 Mile Island. What was the negative outcome, the adverse outcome? It was very much focused on radiation, long-term and short-term, on-site and off-site. That was how, and there's a tradition in nuclear power. It was very, very focused on potential increase in cancer and that sort of thing. What was not recognized, completely ignored, was the impact on nuclear power in the future. Nobody said, oh, this kind of rare event, it could not have the effect. Look what it did to nuclear power. That is a fact. It's not an opinion. That is what happened. It was completely ignored how it could impact an entire industry. How did the failure of Fukushima impact?
Sorry, Bill, I've accidentally
I
muted.
think he's garbled, no?
No, I accidentally muted Bill. I was trying to unmute myself.
Oh, sorry. Okay.
I was trying to unmute to say that you should explain, because there are young people in the room that don't understand what you're saying. So the bad situation at 3 Mile Island sort of destroyed the nuclear industry in the United States, right? So the freeze movement got a foothold, and it just took down. So there haven't been nuclear power plants in the United States for 35 years now because of that.
Yeah, they're just now being built. And so the point is, what is the impact of the consequence, the impact on the assessment of the negative outcome? There's epistemic uncertainty in that all of the time. And one last example, and this is more speculation than saying it was a mischaracterization of epistemic uncertainty. What was the trade-off? How was the decision made at Boeing on, okay, if we have this type of failure, happen to be with the air data system, what is the likelihood that the pilots would not be able to quickly recognize what the situation was? And so that impact on what that has done to the airline industry, and specifically to Boeing, I suspect that they never thought that, they never even considered that. And whether they did a risk analysis, of course, I have no idea. But look at what that has done to air travel, and specifically that corporation. So my point is that I think we need to understand that the epistemic uncertainty in the negative outcomes in the risk assessment is just as dangerous, if not even more dangerous, than estimating an imprecise probability.
Well, I agree with you that that is really important aspect, and that's also why we are not really today thinking about risk as the product of consequences and probabilities, the expected value. You need to see beyond that. I think that is, if you look at what you're doing now, in a more modern way of thinking about risk, is captured what you are saying there. So I follow you 100%.
Terry, I would say very few risk analysts have gone to what you call a modern conception of risk. I see very few people doing that.
I agree, but that's how it is. I mean, the practice is always slow compared to research, and that's how it is. But we still have to argue, and I think that and go on with the processes trying to convince people that you need to see beyond probability times consequences in order to reflect risk, which is really a narrow way of looking at risk. It doesn't capture many important aspects.
Keith, are you, can you unmute yourself?
So I did want to comment about the comment that's in the chat, especially about 3 Mile Island, because to me, I think that's interesting. From the risk that Dr. Oberkamp was talking about was a risk that the nuclear industry itself should have looked at, because they're the ones that care if the nuclear industry goes forward. But you have to remember the regulators, especially like FAA, NRC, if our industry dies, we're not supposed to care. Like, you're only for safety. The FDA, on the other hand, is what's called a dual mandate. So they want that industry to continue. So a lot of times when you see those, I'd say, risks that are having to do with if the industry loses a lot of money, if the industry slowly dies, the regulators themselves are looking out for people's safety, and we wouldn't spend any time there. And to me, that's, I mean, it's kind of interesting. I also kind of wonder, like, I mean, based from what I've seen on the Boeing 737 MAX disaster, I don't think they're suffering any consequences from it. Their stock price fell off, but that was because of COVID. Right around when the disaster occurred, their stock price was about what it was. And now their stock price is almost at what it was before pre-COVID levels. I mean, yeah, they might get slapped with a $20 million fine by the FAA, but I think it was the congressional write-up, they even pointed out when Boeing got slapped with a $20 million fine before, it was the same period they just brought in $20 to $40 billion profit. And so one of the interesting things about, I think, risk is people don't take it seriously until they go through something that has consequences. TMI, I mean, the nuclear industry embraced probability risk assessment after that, and they really started using it. But from Boeing 737 disaster, or the MAX, I don't know that the company's really learned anything. I'm kind of interested to see how the FAA responds. And I've actually done some reading there because there are some good reports. And the thing that I'm kind of wondering is the complete story being told? Because you kind of read, oh, the FAA gave up this and they should have been looking at it, but you dig into it more. And I think that's one of the interesting things for me when Feynman talks about the Challenger disaster. I feel like you actually get to see under the cover, under the hood of when people are actually looking at the risk stuff, what do those people say versus just what kind of gets written up in reports later.
Josh, I fully agree with you on the 737 MAX disaster. There's much more behind that, but that will not come out because of these liability suits that are still being processed. And so Boeing will not release that. I understand they were forced to release some today, but all of that protection in a failure mode like that, absolutely, they're protecting themselves. And your opinion that it hasn't damaged the corporation just by looking at stock price, it's much deeper than that. Are the consequences to the people involved in those decisions, were they adequate in my view? Not a chance. We won't go into what I think the consequences for those decision makers were. That's a different matter. And you could say other high-level decisions that were made based on involvement in management. There are many other advantages, examples: Takata airbags, GM ignition switch, the Volkswagen disaster in terms of what was hidden from the regulator. All of those things, there wasn't sufficient accountability in those things, and that's the why corporations, they're very resilient to that. So that's another matter whether that was sufficient.
Also, Josh, are you on a treadmill?
Yeah, I'm on a treadmill. They're really awesome. I like them. And since no one else is jumping in, Scott, a question I've had for you developing in the back of my mind for a number of years now is, I greatly enjoy the concept of imprecise probability, but I also feel like it's kind of limited because you say, hey, now you have to know these bounds. And I feel like imprecise probability is one example of a bigger field of imprecise probability where you don't know the distribution. You may know some information about the distribution. You guys have greatly developed if you know the bounds of the distribution, but it seems like there should be some other things there. Like, well, what if I only know the mean of the distribution. I don't know the shape or anything like that. And it's just, I mean, and I'm trying to think of like, okay, well, what are some good examples of that? I haven't come up with any physical ones yet, but I do know that there's times when it's like you may not even know the bounds, or maybe you just know one bound, or there are 3 numbers from it. Yeah.
Yeah, there are methods even within P boxes. There are methods that you can use that you don't even have. You don't have any more information than, say, the mean and the variance. You know, if you can constrain those, then it turns out there are these distribution-free sort of P boxes that work. But also there are other methods altogether, like the Dominic Rose's sort of possibilistic approach would suggest that, you know, or Jakob Benheim's infogap approach, where there are no bounds. So just the bounds grow to infinity. It's just a matter of where you want to stop. Both of those approaches can be sort of direct, or I guess all 3 of those approaches would be direct answers to the question you asked. But I actually want to circle back, if Terje is still on. Oh yeah, there you are. About this, so the subjective element. I know you're very passionate about that, and I certainly understand the need to include that information. But at the same time, I go to these meetings at EPA and other places, and people, they roll out the expert elicitation bandwagon for everybody to jump on, and they jump. Everybody jump, because what are you going to do if there's no data? You got to get something, so they jump on the bandwagon. But I call expert elicitation, sort of the great frontier of making stuff up, because there's no. It doesn't seem like there's any way to police, to sort of monitor, to validate what we're doing, at least seemingly. I know that some people have tried, Roger Cook and people have tried to do validations with expert elicitation, but they seem quite unstructured so far. Don't you agree? Or I mean,
I agree.
The traditional way to handle expert elicitation is to build it into the model. It's the modeler's opinions. Is that not okay?
I agree. This is a challenge, and I agree with you. This is why I think that subjective probabilities exact, if you're using that, it can be misleading. It can be arbitrary, as you say, and it's having no justification. So this is why you have to see the context and what is the rationale for producing that. And depending on situation, there may be a rationale in some cases when you have, it can be built on model, and you have to explain what is the rationale for your judgment, and then you can look into that rationale and discuss it. Because for me, it's equally important to discuss the rationale, the argumentation, as it is that number. This is why the knowledge is so important, and this is also why I agree with you 100% that historically, there has been enormous misuse of exact probabilities coming from nowhere and then presenting it as it is the answer with some objectivity. This is completely without justification.
Right.
But it's a research challenge also, how to then get out the most information so that you're not becoming on the other extreme with bounds that are not giving you much information either. So because people have knowledge and how to transform that,
right.
That's the challenge we have. But I agree with you.
I love that your idea about how you would deal with that sort of knowledge that's trapped inside people's brains is not just to use subjective probability, which the Bayesians would be perfectly fine with, but you sort of poke them in the eye and say it should be also imprecise.
yeah, exactly. And I think we have, I have it matured, partly also from our discussions on this. But I think we have developed further to clarify what is then the missing points, and that's how research is working, isn't it?
Yeah. Sure. So, do we come to Francis's question? Do we have things that we agree on? I think we do.
Yes.
Scott,
absolutely.
Let me follow up on the point you made in your slide, and I'd forgotten about it, but Terje just mentioned it again. when if you use traditional probability, or the claim is that if you were to use imprecise probability, that the either the uncertainty estimate or the risk analysis, let's stick with uncertainty. The uncertainty estimate would be, I think the word is usually unhelpful or not useful. As you pointed out in your talk, that doesn't bother people who that have real skin in the game. When you see an extremely large uncertainty, an engineer says, okay, we're going to change the design of the system, or we won't let it operate in that condition. They can deal with that. Yeah. What they do not want is to be surprised about, oh, I thought this was supposed to be a rare event. Well, it happened 1 out of 10 times. Oh no, you completely misled me. So they can deal with very large uncertainties much better than what researchers think they can. The issue is they need to be informed what the real risk is. And so I contend that very large uncertainty estimates, real decision makers that have skin in the game, they can deal with that. They will compensate for that situation, particularly if it's in the design of a system. Or as Keith was talking about, if it is in maintenance of a system, let's suppose it's either manufacturing equipment or a bridge or whatever, you will do preventive maintenance to be certain that that system does not fail like a bridge fails. So I think real decision makers that have skin in the game, they can deal with this much better than what some risk analysts feel.
I agree, 100%. That's a really important point. I mean, I think it's one that we have not been able to present that in a convincing way, because they deal with uncertainties all the time if you are a manager.
Good, thank you, Terje.
I'm writing that down as a point of consensus.
That's lovely. We need to take the victories when we have them.
Uncertainty is important. Yeah.
Yeah.
Hard fought over that one.
That's really good.
But to some extent, it's like similar to what happened in 1917 when the communists took over in Russia, and the opposition in kind of got upset and left. And so, of course, the majority voted. So I wish we had people who are strongly advocating probabilities here now to argue.
I know. We need Daniel. And
there's too much agreement.
Yeah.
Send for Tony.
Yeah.
Yeah, it's a shame Tony's not here. Well, I mean, we've gone over slightly, which is absolutely okay, because we always leave the open discussions to tick over. But in case there's any people that are hoping to leave, let's just thank our speakers again, and then people can remain on the call to continue the conversation if they like. So merci beaucoup to Terje and Scott, and also Keith for their lovely talks and really, really intriguing. So again, please, we're going to keep recording the session just in case there's any comments afterwards, but this meeting has officially been adjourned.
Well, I'll have to leave. Thank you very much. Thank you for organizing all this.
Thanks so much, Vlado.
Yeah, and thank you so much for inviting me, but I've got to go as well. We're in the middle of a big grant application, and I can see the emails piling up.
Pouring in, yeah. It's always manic near the end.
Thanks, Keith.
Thanks a lot, everybody. Bye-bye.
Have a lovely day and a good weekend.
You too, mate.
So were there interesting discussions on the chat? I didn't see it when it happened.
I think just a load of people saying thank you, and there was some kind of internal discussion, but I don't think they were necessarily proposing any questions for the discussion.
The great movie reference was referring to the Arnold Schwarzenegger and movie, right? Somehow.
I believe so. There was some talk of Mario as well from Dom.
Scott, if we don't have any other questions, I would want to pose one. It's sort of a specialty question that I've been asked, and I don't know if I've ever brought it up with you or not. I should have asked also Vlado. The question of the theory, and also Bernardini maybe would be aware of this. If you deal with epistemic uncertainties or imprecise probabilities, this whole issue of the updating procedure when data becomes available, that, at least from my perspective, I haven't seen much written on that in the major textbooks that are out there on imprecise probability. So can you tell me what's going on in that whole field of essentially the equivalent of Bayes equation, Bayes updating for imprecise probability? That seems to be, if you are willing to embrace imprecise probabilities, and then you obtain either new statistical data, expert opinion. So it's really a separate topic from uncertainty aggregation, but let's suppose it is data on the system. Could you maybe, and whoever else is there, comment, because I haven't seen much on that.
Well, there may be people on this call more qualified than me to talk about that, but my understanding is that, well, certainly the Peter Wally and those folks would totally generalize the Bayesian apparatus. So as long as you've got a robust characterization, a creedal set, some sort of robust Bayes characterization, they're still using Bayes. They're still fully Bayes, using the same formula and everything. Just basically doing it on a set rather than a precise distribution. Now, there are issues about updating, specifically, what is it, Grove and Halpern have this amazing paper about conditionalization and how conditionalization, makes perfect sense if you're in a precise probability context. Conditionalization is the only thing that sort of satisfies axioms that everybody kind of agrees are reasonable. But in the IP case, that's not true at all. In fact, there's no good reason to use conditionalization as a model for updating in the IP case, which is remarkable because it directly contradicts sort of what you would expect from the sort of the Bayesians in the Wally camp. And given that flexibility, given that we're free from conditionalization, you could go, there's this thing called radical probability. Have you heard of that? They don't use the definition of a conditional probability, right? So the Bayes rule is based on the definition of a conditional probability. You turn the terms around and that's Bayes rule. There's another theorem of probability called the theorem of the total probability theorem, I guess. And you can turn those terms around and get a different updating rule. It's just different from conditionalization. And it's, believe it or not, there's a Wikipedia site called Radical Probability in which it's described. Seems quite reasonable to me, but I don't know anybody who's in anger.
So you're just one point that you made there. Are you saying that Wally and others that have worked in this, they're
really Bayesians at heart?
Yeah, if you were to use Bayes' rule, I mean, I don't see how you could put those two concepts together, because it's an update given traditional probability, which is extremely defensible within traditional probability. But once you move to imprecise probability, I don't see how you could defend that.
Well, you agree with Grove and Halpern then, fundamentally, but they do it, and the way they do it is just to simply say, well, let's look at all the possible combinations. What's my creedal set that composes my prior, and the creedal set that it's not a set of functions that compose my likelihoods, and we'll do all possible combinations. It's basically an interval analysis on probability structures, and that's how they do it. That's how they produce the results. And the results, of course, are robust Bayes sets. So they're probability distributions, and you can usually draw a P-box around them, for instance.
Okay, so I haven't seen any of this. So you're saying it actually is stronger than what I was suggesting?
Stronger?
Stronger. It's more defensible. It is more in line with imprecise probability, with that openness, with that flexibility. Is that what you're saying, than what I thought it was?
I mean, you'd be hard pressed to call something that's in Wally's book not part of IP. So given that it's in this book and he describes it as, and it's basically just all possible combinations, the sort of the brute force stupid approach, I think. He, at least that's my understanding. Now there is this phrase called generalized Bayes rule, and maybe I've misunderstood it. Maybe there's a different, I can talk at length now that I'm a professor. I can talk at length about things that I just vaguely understand. But the generalized Bayes rule is in Peter's book. But you and Grove and Halpern think that it's like, what? We shouldn't be doing that. Dominic, do you know of any opinions in this area?
So we're talking about updating, right?
Updating, yeah.
I can only advertise myself a little. I'll present a paper at ICIPTA on possibilistic filtering, which is recursive. It's basically an updating procedure, which is kind of like the general idea is closely linked to what Ryan Martin's doing with his inferential models. But I have the book here. I don't think he's saying anything. So what Ryan Martin's doing is basically possibility theory. He just didn't know when he was writing the book, but I think he found out now. But I don't think he's talking about updating actually in the book. So I don't see it.
He's just talking about inference as far as I'm aware, right?
Yeah.
I mean, there's always the default position that frequentists have, which is, well, you get more data, then you redo your analysis and get a new answer. What's the problem? Right? There shouldn't necessarily be a special procedure called updating in which you have your answer and then you tweak it, your answer. You could just take that new data, pool it with all the other data you had to start with, and recalculate the analysis. The only reason that updating is considered so cool and important is because Bayes have this recursive rule. If they didn't have that recursion rule, nobody would be talking about updating. They'd just be talking about redoing the analysis. Don't you think? Or am I being a little glib?
And maybe I'm saying something stupid, but if you have data, why would you use the imprecise probability framework? If you can update a model, it means that you can run experiments or you can gather data. Why don't you use the traditional?
What if your prior was imprecise, or what if your data set was really tiny, like you had 3 points, not 300 points? But
still, you can maybe infer different probability distribution functions, and you get a set of distribution functions.
Yeah.
And then you can update each of those distribution functions according to the traditional Bayes updating.
Yeah.
I don't know.
I think that's plausible.
So I imagine the problem is when you the problem that Bill initially mentioned. I think it's when you have intervals or something like that, and then like pure interval, it's pure epistemic, right? How do you update that? And yeah, I think that's tricky. But if you can update a model, why don't you just use a set of distribution functions? You don't need intervals. Here you can do PBA, right? You can have a family of distribution functions with different means or different standard deviations, and then you update each of them accordingly. I don't know.
Sure. And so you would allow sort of a robust Bayes.
Yeah.
Right. If the data were intervals themselves, then you kind of have to be robust Bayes.
Something like that.
Yeah. Yeah, I think that's. Well, I don't know anybody who thinks that's unreasonable except maybe Bill.
Can I ask a question about that? Because I mean, in your talk, you talked about the false confidence theorem, which I've been meaning to read up on it, but I don't know yet. So, but I guess that with lots of data, you would, in that what you were just now talking about, you would eventually converge to some sort of precise posterior distribution, which would then again suffer from false confidence, would it not? So it's
if the measurement
really
was big, it would, yeah.
Yeah, so yeah, this is, I mean, this is kind of circling back to what you initially said, that the Bayesian approach itself is maybe flawed. I think you said that, right?
I'm a Bayesian. Aren't you a Bayesian? Everything's a Bayesian.
I'm not sure if I'd call myself a Bayesian.
It says Bayesian approaches have many advantages, actually. We should, I mean, it's kind of weird that I would be the champion of Bayes, but it does have many advantages. And in truth, as a statistician, if you deal with data, a lot of data, precise data, and you have a lot of it, I don't know why you wouldn't be a Bayesian. It's the natural thing. It's very efficient to be, right? The problem is in these rarefied situations where we just have no data, or we're making up new schemes, new models because we've never had this implementation before. We're going to a new planet we've never been before. In those contexts, Bayesian methods are less reliable. That's all.
Yeah, this is something I wanted to ask with this digitwins that people try to, well, at least in my case with nuclear fusion, people try to merge together physics and engineering models and then pretend to have a digitwin of something that doesn't exist. So how can you trust the numbers you get from that model if it's something that you have never built before? I think the same applies for a base on Mars or on the moon, right? It's like, yeah, you have some physics here, some physics there, but when you extrapolate from the computer, like maybe you're missing some unknown unknowns, and well, maybe no, I'm pretty sure you're missing some of those. How can you trust those digitwins?
I think nobody trusts digital twins, especially the people who work on digital twins.
Yeah.
But I mean, certainly there'll be some situations in which they'll be useful. I mean, in the old days, engineers used to build physical twins, right? I mean, they built two lunar landing excursion modules. They sent one to the moon, and they kept one in, I guess, JPL or Houston, and worked on it. When they had to answer questions about the device.
Yeah. But well, yeah, I'm not sure if I have something else to say. They still build prototypes, yeah, indeed. But there are some cases where you can't build prototypes.
Sure.
Or cheap prototypes that you can destroy or test. And I think that's the argument that people use for digitwins, right? It's like, well, we have some systems that we can actually prototype because they're very expensive or very time consuming. So we go and we build these computer prototypes instead to do experiments over them.
I think that's mostly it, yeah.
Let me make a sort of a historical comment on digital twins. I think I have similar opinion what Scott said there. People that really make decisions on them, they don't trust them, and that's fine because they're the ones that have to make the consequential decisions. But the root ideas come from situations, as Scott said, where you do have a tremendous amount of data. And in my background, more on the aerospace side and aeronautical systems, the reliability of gas turbine engines, particularly on aircraft systems, but also on land-based systems, on power generation systems. The database for individual blades on either compressor, individual rows, individual blades, and on the turbines, and on the disc themselves, but particularly on each blade in a gas turbine engine. The history on every one of those is known exactly. The manufacturer keeps track of it. Every blade is known, and its cycles are known, where it was made. All of that data is captured, and they continually do updating when they have to replace blades, because if you lose a blade, either in a compressor or in a turbine, but especially a fan blade, you are in an extremely dangerous situation. So that idea of digital twins comes from the statistical side, where you have a tremendous amount of data. And it's a very solid basis. And that's why the reliability on gas turbine engines is unbelievable. And that is why it is there. It's a combination of both physics-based models, finite element models, on the blades and their history on how many times they go through all the cycles from the throttles. And all of that is kept. So it is the perfect combination for a digital twin, but it is for a very small piece of a system. And you could say it's complicated, yeah, but compared to a complete engine or compared to an aircraft, it's a completely different game. But right now, digital twin is a new marketing term, and of course, a lot of people are pushing it. But we need to respect how far we would move from that concept, very restricted concept on a simple system, to a very complicated coupled system. So I just want to make that little bit of a history comment, and then in a few minutes I want to have to head off. So that's where it has worked very well.
And I was going to suggest, actually, it's probably time for us to adjourn. We're well past our time, and Francis has to eat at some point. So thank you, Francis, for hosting us and for organizing.
No problem at all.
Yeah, thank you.
Always a pleasure. And I'm glad that we got some really good feedback on the chat, and we'll be uploading the talk later on for people that want to rewatch it or send it to people for them to see, and for those that couldn't attend. So please spread the word, and it'll be available on the Risk Institute Vice website.
Thanks very much.
All right. Take care and have a lovely weekend, everyone.
Thanks, everyone.
Thanks.
Bye-bye.
Thank you very much for the talk.
Bye.
Always nice to hear from you.
Dominic,
All right. See you later.
Dominic, are we convening at the other meeting?
I don't know if we can talk if you want to.
I can leave the meeting room open if you'd like to talk here.
Made me a host, so you could probably leave.
Yeah.
Yeah.